Hello, my name is Wendy. I'm a software engineer at Red Hat, and I'm part of the Anaconda team, and I've been the lead developer of the Anaconda backend. Welcome to my presentation about the story of the Anaconda backend. Let's start with a simple question: what is Anaconda? Anaconda is a system installer used by used by Fedora, RHEL, and other operating systems based on this. It kind of is doing three stuff. So usually when you want to install something on your system, you download an ISO, put it on your USB stick, boot it, and then what happens is that Anaconda configures the runtime configuration, so it modifies the installation environment based on some preferences and detected values. Then it tries to collect the user preferences about the final system, so you can select what kind of language would you like to see on your system. The time zone, you can choose some specific software you want to install, define the partitioning, and create some user accounts. And then we verify that this is valid, and it looks like the new system should be viable and bootable and usable. And after that, we allow to start the system installation. And this is important because while we collect the user preferences, we don't really touch any of your disks, and we don't modify your data. But once you confirm that you want to start installation, that's where all the magic happens, and we use your user preferences to do some real actions on your hardware. So quickly, how does it look? So the runtime configuration usually happens in very early stages. You usually don't even see the screen because it happens very quickly. Then eventually you end up on something like this, where you can specify what you want to do. As I said, nothing really happens. We just collect your data, and when we have all that we need, we enable the begin installation button. And then we actually do the real action. Why I'm mentioning this? Anaconda is very difficult because of this part, like the part where we just collect stuff, but we cannot really actually do some stuff because we have to kind of simulate what's going to happen and how the system is going to look like, and that's not easy. And also you can like visit and configure anything in a very random way. So you can start with the user account and then specify the software and then specify the partitioning, but in reality what happens next is that we start with the storage, download the software, and then we start to create some configuration. So yeah, this is the difficult part. So what's the actual Anaconda modularization? So this is the initiative that started in 2017. And the idea was pretty simple. So we started with something like this, and that was one huge monolithic Python application that had everything in one process. So the user interface had access to all the data that you might need or you might not need. Everything could use anything, and it was all very interconnected, and it was just a huge mess. So the idea was to separate this that data and business logic into dbus services, and have the user interface and the dbus services, and the dbus services can talk to each other, and user interface can talk to dbus services. What will you gain with this is that eventually you can replace the user interface with something that's not even based on Python, and for example have the web-based UI, which you might have heard about this year. So yeah, the idea of the web UI is very old actually, and it started here in this year because it was the ultimate goal to get there. So that was the plan. What was the reality? So this is kind of what you have. Like Anaconda is a very old project, and it's not pretty. So there are like no nice boxes that you could just take and move to some service. You have to create these nice boxes first. So you just start somewhere. So let's say you are able to identify a piece of code that looks kind of isolated, and maybe you might be able to move it on dbus. So the next thing you have to check is what kind of data does it use. And if there is anything that's not really on dbus yet, you cannot really touch this logic because you would miss the data. So instead of that, you target the data see where it's used, and migrate the data first. Make sure that all the code that uses this data are using the dbus API to gather them and change them. And then you actually can go back to the piece of code that you wanted to move and move it. So based on that, we targeted the data. So Anaconda had a lot of weird data objects for some reason. So yeah, we had a lot of global variables. That was lovely, but we eventually got rid of them. Another weird object was the Kickstart data. So Anaconda has like this special mode when you can like automatically run the installation using a Kickstart file, and Kickstart data is like a Python representation of this Kickstart file. But the Kickstart data are used also for interactive installation because we use it as a main data holder of your preferences, which doesn't make sense because Kickstart doesn't support everything that Anaconda does, so you end up with a lot of workarounds, and that causes a lot of issues. Another funny object that we have is the storage model. So as I said, the storage model is, so we have to somehow like simulate the actions first. So with the storage model, we have a Python representation of your device tree, and we do actions on this device tree, and we just check the result. And when we are happy, we actually apply these changes to your real storage. But unfortunately, our storage model didn't have an undo button, but sometimes you had to like reset because you ended up with a very invalid model. But this object was already propagated to all corners of the UI, so you couldn't just throw it away and create a new one. You had to somehow reset it, and that was also an issue that we solved later in the modularization. Then we had a representation of the payload object. By payload, we call like all the support that we need for installation software on your system. And then there is a special category of product data where every product can have a little different defaults that they want to show users. So that's also something that we need to take in account. So the most problematic part was the Kickstart data, actually. So we decided to start the planning around that, and we collected all the Kickstart commands that are supported by Anaconda, and we split them to some areas that made sense. And this is basically the foundation of the dbus modules. And you finally have something to work on. It has very clear goals, and you just go module by module, command by command, and just try to figure out how to like handle this command via the dbus module. So this was the plan. The phase one targeted the system installation, so everything that you needed to actually finish the installation. And the phase one was actually finished on April. So yay, we are done with this one. The second phase is going to target the runtime configuration. It's about the runtime module and the bus module. The bus module is kind of special because its main purpose is to orchestrate other modules and send them some data and collect some data from them, and basically it like oversees the whole dbus API. So what kind of challenges did we face? So the first question was, where will we develop this code? And we had two options. The first one was to have a development branch, which would be separate from the production branch. And it would be nice because if we make a mistake, it will not affect any critical workflows like Fedora Rawhide. Unfortunately, it means that until you release this thing, you don't get any feedback about what you are doing. So you don't really know if your idea of how it should work really works in the real world. Another thing that we were afraid of was to keep it in sync with the production branch, because this project didn't have a very high priority, and there was always like new stuff and features and requests that were coming up, and we still continued development of the production branch. And we didn't want to lose these features and bug fixes, so we would have to port everything to the development branch, and we knew that that would be just too much work. So the other option was to use the production branch, and that has a lot of benefits, but unfortunately, you can very easily break Fedora Rawhide, and you don't want to do that. Yeah, so there was like a lot of pressure about making it right, and we were doing very thorough request reviews, and yeah, we spent most of the time on just making sure that we didn't forget any use cases before we actually did some change, and that was very difficult to do. But I think, like, considering the amount of work that we did, we didn't mess up so much. Yeah. So what we had and have for all these years was kind of a hybrid solution. Because, I mean, some of the Kickstart commands were migrated on the dbus modules, but a lot of them were still handled by the user interface. And that created a lot of interesting situations and challenges, because you somehow needed to take this Kickstart file, tear it to pieces, send it to the right components, collect the feedback about possible issues and validation errors, and later again collect new pieces of this Kickstart file and generate an output Kickstart file. Another thing that we had to make sure is that there is no overlap, that we didn't forget to remove the management of one Kickstart command from the user interface, but while it's already handled by another dbus module. So we wrote a lot of unit tests for that to make sure that this is fine. Yeah, another challenge that we had was how to quickly and safely develop the dbus API. I don't know if you ever read the dbus specification. Don't. You will. It's really difficult to like understand and grasp. So we needed to make sure that what we are writing is right, and that we don't have to spend a lot of time on like these little tweaks and weirdness of the dbus API, and that we can focus on the code. And we knew that we will develop this very like in iterative way, and that's going to be a lot of refactorization of the dbus API. And for example, one of the things that you need to provide at some point is like XML specification of your dbus object, and that's really not something that you want to refactorize because it would work. So what we actually did, we started with the PyDbus library, but we built a lot of functionality around that would simplify a lot of stuff for us. And eventually we threw away the PyDbus library and created a new one, which solved some other issues that we had with testing, for example, and put there all the new support that we created. And now it's available on pip and other operating systems, so you can use it if you want to. So another issue that we had was the management of the default values. So the problem with defaults is that we have a lot of sources of the default values. I mean, like Anaconda has some ideas what are the defaults, but then the products have some like other ideas what the default should be. And then you have like these kernel arguments and boot options that can override them. And we didn't want to like propagate all these sources to the dbus modules so they can like pick one. So instead of that, we introduced the Anaconda configuration files that are just text-based, and we, in very early stages, process all the sources and some point generate a temporary runtime configuration file, and then we start the dbus modules. And the first thing that the dbus module is doing is that it's looking for this new runtime configuration, and it's using only this one. So it doesn't have to care about the other sources, which helped us a lot. And the final question was, how can we test the thing? So the main goal was to be able to test the backend with unit tests very easily. And luckily, we were able to do that with the libraries that we had. So we didn't have to like do any weirdness with dbus daemons, and we didn't have to like test really the dbus API. We could just create these Python representations of the dbus API and unit test them directly, which simplified a lot of things. What we also were focusing on was the end-to-end testing. And with Anaconda is very difficult to test, so this was like the best effort we could do, and that was the focus on Kickstart tests. But that was actually good because we were targeting Kickstart commands. So it makes sense when we was migrating a Kickstart command like autopart, and it wasn't covered by these end-to-end tests, we could write a new end-to-end test to make sure that it's covered forever. So we spent a lot of time on this and improved the infrastructure a lot, and it was also great. What's the current situation. So as I said, we finished the first phase, and this is the code distribution of our current modules. As you can see, storage kind of consumes like most of that code. Then it's payload, network, and the other modules are pretty small. So you can guess that we spent years on the storage development and another years on the payloads module, and then the network, and the other stuff was pretty much easy. So here are some milestones, and yeah, it took forever, but as I tried to explain, there were reasons for that. So what were the benefits, and was it like even worth it to do this horrible mega thing? We have a pretty good code coverage of the new code. So this number is a little confusing, but we can check actually how does it look like right now. And when we focus on the PyAnaconda library, which holds most of the Python code, you can see that the core package, that's like a general library of functionality, has a pretty good coverage, and the modules have a pretty good coverage, and UI, yes, we don't have tests for UI, so obviously not so well. And the modules itself, most of them have a very high code coverage, except for the ones that are really big, like the network module, the storage module, and I forgot the last one, payload. Oh, payload is pretty good. So yeah, I think we did a pretty good job. And when we started, I think the code coverage, we didn't even measure code coverage, but I think it was around 20%. And it wasn't great. So what's next? So the number of end-to-end tests that we run daily on Fedora Rawhide with our upstream changes is over 1,000, which is a lot, because when we started, these tests didn't even work properly. So like having these run daily makes me sleep at night. So another like side effect of these things was that we kind of by accident stabilized the GUI and TUI, like the current user interfaces. Because when you are like modifying the user interface to be able to interact with the dbus API, it means you have to touch the code and you have to test it. And if you find a bug, it doesn't make sense to ignore the bug and leave it there, you fix it. So we were like finding a lot of issues there and fixing like a lot of bugs just by like working with this piece of code. And then when we had the bug reports, for example, for RHEL, we noticed, okay, but we saw this on upstream actually, and we fixed it. So it was very easy to just port the fix to RHEL, and it didn't cost us any additional work. So this was great. Another benefit of the development of the backend is that it enabled the development of the web UI, because web UI wouldn't be even possible if it didn't have something to talk to. So this was kind of crucial part of that, and the fact that we can work on this is great. But as I said, this all started years ago. Another thing that we improved is the simplified way of customizing Anaconda for products. As I mentioned, we had some issues with that, and we had to handle defaults differently. And side effect of that is that it's very easy to like provide new defaults for your project. And you don't have to understand Python. It's no longer a weird Python class that's breaking all the time. It's just a simple text file that everyone can understand and change. And you can find it in our repository. Another thing that this was intentional, was that the support for add-ons is much better on the backend level. And basically, there's almost no difference between add-on dbus modules and our dbus modules, because they use the same basic, like the base API, and we treat them the same. So we were able to like remove some weirdness around it and make sure that it's easier to develop. Also, add-ons can now be developed in other languages if you are interested, because it's dbus and we don't really care what's running behind it. So that's another nice thing. And one controversial thing I want to mention is that, so since we kind of like dropping the dependency on the kickstart data object, the data holder, and using kickstart just for input, and it's no longer just there to hold some data, it means that there's a possibility to support more formats or maybe switch the format or stuff like that, because we don't really depend on PyKickstart so much anymore. And I personally don't like the current format. So if anyone is interested, this is definitely something to think about, because I think we could do much better. So what's the future of this? So right now, my colleague is working on the phase 2, which means he's writing debug support for the runtime configuration. In the future, we want to clean up and stabilize the debug API, because it's a little still rough and messy. Still, it was code that was developed for 6 years, so some of the early parts are not so nice as the later parts. And also, we have 0 documentation of the debug API, which is not great. Unfortunately, all the resources are currently working on the web UI, so I cannot promise you when we will have documentation of the debug API, but we will get there. Yeah, so that's all from me. I just very quickly, because I have time. So like one of the side effects of this was that we created some new libraries. As I mentioned, we have the DasBus library for the debug communication. And there's another library called SimpleLine. And that's actually a very simple Python framework for the text-based user interface. Because we don't have only the graphical user interface, we also have the text-based user interface. And because of some weirdness, okay, S390, we couldn't use existing libraries. So this is kind of like separated code that used to be for a very long time in Anaconda, and we cleaned it up and created a completely new library that's independent on Anaconda. So you can also use it if you are interested in this. Okay. Here are some additional info. As I said, don't look for the debug API in our documentation. It's not there. If you have any questions, reach out on Metrics. This is the best way how to get any answers. Yeah. Does anyone have any questions? Yeah, okay.
You mentioned the possibility to develop a new Kickstarter format. In addition to this idea, has been eventually evaluated to talk about other open source Linux installers in order to create some kind of lingua franca, one format for everybody, or at least evaluate what is already existing, also inside for example, the Fedora ecosystem, like for example, one for CoreOS, or on the outside, because Ubuntu has recently created its new.
Yeah, okay. So the question, sorry? Yeah. So the question was if we will consider the new format instead of the Kickstart, have we considered to use like the existing formats that are used by other installers? So yeah, this is not really like an initiative. This is like an idea that I'm like throwing out for someone who's interested. But yeah, it would definitely make sense to look at what's there first. I personally would like to be able to use Ansible, but we kind of looked into that, and it would be so difficult to support that. But yeah, it makes sense to like try to unify the formats and make it happen. Yeah, please.
So, kind of a springboard on this other question. With all this work that you've done in the Anaconda backend, have you considered writing some kind of simple command line interface to execute all these things in series, as if you wanted to simulate a workflow running through the web UI, or through another front end that somebody else would develop, or something of that sort? Because the OpenSUSE guys, when they wrote Agama, their first interface wasn't the web UI, it was a CLI tool that they could invoke the services in sequence. And they used that to be able to build all the other front ends on top. That allowed them to document the dbus interface, because they used the dbus interface as the parameterization and do those other things.
Yeah, okay, so the question was difficult. So kind of, if we considered to create the client, a simple client that would allow to run the processes first and then write the web UI based on this client tool, right? Yep. Yeah, okay. So, no. So basically, like, Yeah, you kind of have like very limited resources, so you have to like explain everything what you are doing, and there wasn't really like a need for this kind of tool because there are like other tools who are better at just like doing the installation in non-interactive way, and Anaconda's focus is the interactive installation. So like it's definitely possible to use the backend and write a very simple tool that will just use the backend without any like user interface. But there was no demand for that, so we didn't really explore this area.
That would have been a way to do it with Ansible too. Having that simple interface, you could then plug it in as an Ansible module and just run it through. You wouldn't need to figure out how to define unintended installations. Anyone can just do it for you.
Yeah, definitely. Yeah. Well, there was no demand. Like no one asked for that, so we couldn't just go and like write this piece of code that no one really needed at the point. Any other questions? Yeah.
So browsers don't code debug, so how the application, the JavaScript application, I assume, talks to the debug interface? Do you use something like the cockpit's bridge, or have you created something on your own?
Yeah, okay, so the question was about the web UI and how the web UI is actually talking to the debug services, which is a very good question. And yes, we are using Cockpit Bridge and basically the whole cockpit set up to communicate with the debug services because the support is already there. It was very easy to reuse for this use case. Yes.
So when I came a little late, so I apologize for covering this, but when I installed Fedora 38 today, or the next version before, how much of the debug backend am I using?
Well, you are using all of it because, yeah, maybe you were not there. So basically, we were like doing this iterative way. So we were like we were doing the migration over the years iteratively. So there was more and more backend. And since we finished phase 2, it means that most of the or all the modules that are related to the system installation are basically finished. So all of that is running via dbus. The missing parts are just very simple edge cases that are related to the runtime configuration, and that's currently being worked on. But otherwise, it's all on dbus, and it mostly was dbus for years. Yeah. Yeah.
Do you currently have any idea what time in the future we might be project might be ready enough to leave the hybrid model and move completely to the dbus code base?
Yeah. So the question was when we will be able to leave the hybrid solution and fully switch to the dbus modules, and we should be able to do that at the end of the phase 2, which is currently under development, because the phase 2 is targeting the missing kickstart commands, and once all of these commands are handled by dbus modules, we can like drop all the support in the user interface, and the user interface should use only the data in these dbus modules. And it's also critical for the web UI as well, because it cannot really access any of these data that are not available on dbus.
Okay, so 80% code coverage is pretty okay. But have you ever considered that spending like this, I don't know, a few months of development time to develop it with the code coverage to 90+% would save you a lot of stress from considering all the scenarios that you could break when developing the modularization like way?
Yeah, so basically, I guess the question was why the coverage is not higher.
Inside, it would save you actually time from your PR reviews or considering all the use cases if you actually spend prior to developing more time on covering all the scenarios that you didn't have covered.
And do you mean the unit tests or the end-to-end tests?
Like all of it. I guess I don't know what code coverage actually involves.
Okay, so the code coverage is related to unit tests, and you really don't want to write unit tests for something that you are going to refactorize like 3 weeks later. So as we moved a piece of code to the module, we tried to cover it with unit tests. But since Anaconda is very complicated and it's a lot of code, really, it's really like 100,000 lines of Python code. It's not so easy to cover all edge cases. So I would say we did our best, and this is what we have. But there's definitely space for improvement, and it can be better. Yeah.
I'm going to preface my question with a comment. I'm not Williamson myself.
I know you.
I just wanted to say I think you've done an amazing job of this. I'm the guy who tests this when they're done building it, and it's amazing to me how well it's worked the whole way through this kind of slow development process of switching to Diva, so great job on that. And my question is, as you've been going along doing the Diva stuff, have you considered dropping support for certain difficult to maintain things, and how have you made that decision?
Okay, so the question was if we were considering dropping some difficult support, and how was the process of doing that. So what we were able to do is that we very often found something that didn't work for years. So we kind of silently dropped it because no one was complaining that it doesn't work. But sometimes there were people who later noticed, so we had to like say, okay, it's gone, sorry, we are not reviving that. About like specifically targeting difficult parts, I guess it never was on the table. I guess we always try to support all the use cases that we had, which maybe we shouldn't because yeah, it was sort of work. Yeah, that was kind of it. We didn't really try to like target some stuff that were already working because we were afraid that someone will complain that, okay, but this used to work and now it's not there and you did a horrible. Yeah, maybe we shouldn't. Another question? Okay, so thank you so much for coming. I hope it was interesting and so much fun.
Guys.
Thank you. Hopefully you can hear us. Welcome to DevConf. Welcome to our session. So my name is Victor, this is Artem. We're both from Red Hat, from the core kernel team. And we'd like to tell you something about what happened in the BPF world in the past, let's say, 1-2 years. Let me start with a bit of statistics. You can see the number of commits and the number of changes in the BPF subsystem in the kernel throughout the past 2 years. And you can clearly see that the trend is rising. So BPF is really getting a lot of attention upstream. There's a lot of new work appearing practically every day. At the beginning, when we set up this talk, we put down everything that we found interesting that happened in the past 2 years, and the overall talk took like something more than 1 hour. So we had to pretty much cut it to less than a half to match the schedule. So we won't be covering everything, but we'll be covering the most interesting parts from our point of view, which are especially interesting to people who try to develop their BPF applications. So maybe let me first start with a quick poll. How many of you have ever written a BPF application in any sort, in some framework, whatever? Okay, not much? Cool. So this talk will be quite technical, so hopefully you have at least some basic knowledge of BPF. Let me first maybe do a quick recapitulation. What is BPF or eBPF? I'm gonna use these two terms like one. Today, eBPF equals BPF. So basically, it's an in-kernel, let's say, virtual machine, which allows you to run your own programs inside the kernel with kernel privileges. Those programs are written using so-called BPF instructions. It's a special language for that. And one of the most interesting parts about this is that there's a component called BPF verifier, which checks every program that you try to load into the BPF subsystem, into the kernel. And it checks that the program that you're trying to run, or you will be running, is safe to be run inside the kernel. So it doesn't crash the kernel, obviously. It doesn't hang the kernel, so the program must terminate, and so on. This is quite a strict component, and we'll be talking about it a lot today, so that's why I'm mentioning it. So once you have your eBPF program loaded into the kernel, you can attach it to various events in the kernel, such as kprobes, sockets for some network filtering, C groups, and so on. There's so many probes that you can, or there's so many events that you can attach BPF programs to these days. Okay, we're gonna split the talk into several parts. And the first part is we'd like to introduce you some new features that you have as BPF program developers that you have available and you can use to write your BPF programs, or you enhance your BPF programs. So first of all, one of the most interesting things that happened in past years in BPF are so-called BPF kernel functions. If you've ever written a BPF program, you probably know that it's not easy to call kernel functions from BPF programs. You can't call anything, because obviously that would be too dangerous. So the first way to approach this are so-called BPF helpers, where the kernel contains a list of functions which are allowed to be called from BPF programs. They were quite difficult to be added, so the list of helpers didn't grow much throughout the time, but there was found that there's a necessity to come up with new functions that can be called from BPF programs. That's why the concept of BPF kernel functions was created, which are much more easy to create and edit. You basically just need to annotate the function inside the kernel with this special annotation and register the function for the correct program type, and you can then call the function from your BPF programs. One of the nice things about kfunctions is that the verifier, they allow the verifier to perform additional checks so that it can check that usage of these functions is safe inside your BPF program. This is done through, again, another annotations. I will be showing an example of those in the next section. Maybe an example would be great. So we have one example, by the way, which was written by Artem here, where he added a new kfunc for calling the crash kexec function. it was as simple as this. So he basically added this function to some list of functions, and then this list of functions is registered to be allowed to be called from certain type of BPF programs. What this allows you to do is that you can, when you're writing your BPF program, you just declare this function as extern, and then you can actually easily call it from your BPF program. Which means, in this case, you can crash the kernel from your BPF program. Sounds interesting. Is that anyway useful? Well, quite yes, because you can crash the kernel in a controlled way. You can let your BPF program simulate some situation that can happen in production, then crash the kernel, which will obviously give you a crash dump, and you can then analyze that crash dump afterwards and maybe find some problem that you wouldn't be able to simulate otherwise. So this is one of the use cases for kfuncs. Another concept of that appeared in BPF recently are so-called reference pointers. One of the problems is that BPF programs work with pointers is complicated because the verifier had to check every time that the pointer, the referencing a point, you can only access memory which is available to you, and there have been a lot of problems with accessing memory from BPF programs. One of the ways to approach it are so-called reference pointers, which are actually implemented using the kfuncs, that's why I started with them, and that basically allow kfuncs, or functions from the kernel that your BPF program is calling, to return you a pointer which you can then dereference and use it to access memory. There are two kinds of these functions. One are annotated with the acquire annotation, which says that this kfunc is returning a reference pointer, and then the other one is tagged with the release annotation, which says that this kfunc is releasing a reference pointer. These work roughly the same as the references in other languages. So the verifier, or there's a component which is counting the references to the pointers, and you can be sure that the pointer is not freed, or the pointed memory is not freed during the time you have acquired this pointer. If you didn't have this, every access to memory from a BPF program had to be done through a special BPF call, which would register an exception handler because the memory could have been freed and so on. This mechanism allows a much easier and straightforward access to memory by actually holding a reference to the pointed memory, which prevents that memory to be freed in the meantime while you hold this reference. So as I said, the verifier is checking that this reference is always valid. But one of the problems that was created by this is, what if you want to acquire a pointer and then you want to use it from a different BPF program? Is that even possible? Luckily, it is, by yet another concept of so-called long-lived kernel pointers, which are new kind of BPF pointers, which have several features, such as they must be strongly typed, they are returned by the kfuncs or by the helpers, and that may be stored inside BPF maps, which is the most important feature, because then you can acquire a pointer, you can store it inside a map, another BPF program can pick up the pointer from the map and dereference it and use that memory, and you can be still sure that the memory is not freed in the meantime. Actually, there are two kinds of long-lived pointers. There are the reference ones, which are more important or interesting, but there are also unreferenced, which still can be only accessed with proread. So this is basically plain pointers without reference counting, which you can just store into the maps, but you have to still use this special proread call to access the memory. However, you can also use the reference pointer inside maps. They can be safely dereferenced without proread, and they are automatically destroyed once the map is freed, which is the nice part. So there's sort of automatic garbage cleaning. You have a pointer, you acquire it, you pass it to a different BPF program through a map, then this program works with it, then it doesn't free, it doesn't matter, because once the map holding the pointer is freed, the pointer will be automatically destroyed. Okay. As I said, there will be a lot of technicalities in this, and this will be quite packed, so sorry if I'm going too far. Oh, sorry, too fast. Anyway, another concept that has always been troublesome in BPF is iteration. As I said at the beginning, one of the things that BPF verifier is checking is that your BPF programs do not hang. They must always terminate. This is a problem. It's been approached in a different ways throughout history. First of all, we basically said there can be no loops in BPF programs, which works, it's efficient. However, it's quite too constraining, as you can imagine. The second approach was we allowed to unroll loops by the compiler, which works again, but it's quite impractical. So another thing that came up was that BPF subsystem allowed fixed iteration loops. So loops that had a known number of iterations, but still they were quite difficult to verify because the verifier had to walk every path through that loop, every program path through that loop, and check that indeed the number of iterations is still fixed. So one of the most recent things that appeared in BPF is this BPF loop helper, which resolves this problem because it's a new helper which has this annotation, which basically you pass it a number of iterations and you pass it a callback function, and it will execute this callback function the number of iteration times for you, which means that this is something that is very, very easy to verify because the execution is not inside the BPF program. The execution is handled by the BPF subsystem itself. So if you can verify that the callback function terminates, then automatically your loop terminates. And this is a very elegant and much simple to verify way of writing loops in today BPF programs. Another thing that is problematic is that sometimes you want to iterate things that don't have a known number of items, but you know that they are finite. For instance, you want to execute some BPF program for every process running in your system. You don't know how many processes are there. What you know is that there's a finite number of processes, and this will terminate. To resolve this, there is this concept of BPF iterators. It has been around for a while, which are some special probes which are not attached to events, but they are executed for each kernel object of certain time, for instance, for each task, for each file, for each VMA, etc., etc. What is a new thing about BPF iterators are so-called generic iterators, which allow you to very easily add new iterable objects by a concept which is very similar to iterators in, for instance, C++, where you just specify these four things. First of all, you define a structure which will hold the iterator state, and then you just define three functions, one for creating the iterator, one for getting the next item in the iterator, and one for destroying the iterator once your iteration is done. And this way, just by registering these four functions, you can create a new iterable object inside the kernel. Quite an elegant thing. So last thing in my part is this multi-link attachment feature that has appeared in the past year or two. One of the problems of BPF programs is that they sometimes take time to attach, especially if you're trying to attach one BPF program to many events, such as to all the syscalls. There are some 300 and something syscalls on standard machines, and if you want to attach one BPF program to happen anytime a syscall is hit, it can take some time. So there is this new link type BPF trace kprobe multi, and this concept is implemented using fprobes, which is a bit similar to kprobes, if you know kprobes in the kernel, but it's built on top of ftrace. The difference from kprobes is that it's available only for function entries and exits, so you cannot attach to arbitrary instructions, but it allows you to very quickly attach to multiple functions. I have an example here where this is I'm using the BPF trace tool to attach to all the syscalls. You can see it's some 426 probes, and while it took some 15 seconds to attach in the past version, with these new probes, it takes less than a second to attach. So a major speed up tools or programs that you want to attach to many probes. Okay, that's everything from my part. We'll have to pass the mic, so if you have we can answer one quick question while we do it.
Unmute? Does it work? Yeah. Okay, so now let's talk a bit about BPF inner workings. First, I'll talk about memory management, and there were a couple of interesting developments here. First is BPF-specific memory allocator and allocated objects and linked lists that it enables. And another one is BPF proc-pack allocator. BPF-specific memory allocator was introduced by Alexei Servoitov, and it's used for dynamic allocation of memory in BPF programs. Obviously, there are already a number of memory allocators in kernel, but none suited BPF programs well. And that is because memory allocation in kernel depends heavily on the context it's run from. And BPF programs, especially the tracing ones, can be run from any context, including NMIs. It's a common problem with memory allocation, and there are common ways to deal with it. One is known as memory pools. And the idea is you pre-cache some memory in a non-restrictive context and then use it when the time comes. So BPF memory allocator does exactly that. It creates optionally per CPU caches of objects of predefined size and manages them through IRQ work, which is a relaxed context. One of the issues with memory pools is overextending memory, using more memory than is needed at the time. So Alexei tried to remedy this with high and low watermarks to keep the number of cached objects low. The interface is pretty simple. You get basically two pairs, one to work with variable size objects and another one with predefined size. And as you might have seen, this needs a reference to struct BPF memlock, and you need to initialize it in advance and destroy it when you're done. You can define whether you want it to be per CPU cache or not, and the size of the objects. Okay, there are some real-life applications already. The page set that introduced this allocator also switched hash map implementation, dynamic hash map implementation to use it, and it claims 10 times faster dynamic allocations now. It also allows sleeping and tracing BPF programs to use dynamic hash maps, which wasn't possible before. A bit later, another page set switched BPF local storage to use this new allocator, and that fixed a deadlock problem when BPF local storage was used from tracing programs. It was caused by lock contention in kmalloc. And one of the most important things that it enabled is allocated objects and linked lists. So just a couple of months after BPF allocator was introduced, another page set was posted, and basically that allowed introduced allocated objects and linked lists. The former allow BPF programs to define their own, to allocate their own objects of a type in the program BTF, and basically enable them to build complex data structures flexibly. The former introduced linked lists that are single ownership, and they can be put into maps or disallocated objects and hold such objects as elements. As is usual with BPF, everything is verifier checked, so they're supposed to be safe, at least from the verifier standpoint. Unfortunately, interfaces for these are currently experimental, so I'm not going to show any. But if you want a head start, you can look for examples in self-test BPF directory. And also in that directory, you can find a BPF experimental.h header file, which is kind of a staging ground for these in-development APIs. next is BPF ProcPack allocator. Unfortunately, due to time constraints, I had to cut it almost completely. But the good news is that it's very well covered by WN. And if it sounds interesting, I encourage you to go through these articles. They're very well written. The idea of BPF ProcPack allocator is to first save some memory. And that is achieved by packing multiple BPF programs into a single page. Before this, every single BPF program was using a whole page, memory page. On x86, memory page is 4 kilobytes, and that is way more than usually a BPF program is. It also tried to improve performance by using huge pages and easing up TLB pressure, but due to bugs found in this patch set and also in previous patches that this patch set uncovered, it is not the case. And as of now, BPF ProcPack allocator is merchant working, but it only packs BPF programs into a single normal page. This also inspired some work on generic executable memory allocators. And the first attempt wasn't that successful because it wasn't available on all architectures. And another important user executable memory in kernel is kernel modules. So it couldn't be used for that. So that's why it was decided not to merge it. But just a couple of weeks before this talk, another attempt was posted. It is called JIT/text allocator, and it is currently under discussion. There are obviously some concerns, but it looks much better. Another topic is BPF program signing. This is a long list of small improvements, and it started a long time ago. The first patch set was posted on April 2022, and we're still not there. BPF programs might look similar to kernel modules at first glance. They're both stored on disk as ELF files. They both require relocations. They both require memory allocation and so on. But there is one important difference, and that is in case of kernel modules, kernel does all the work. It understands the structure completely. It does everything. And in case of BPF, libbpf does a lot. So by the time the code gets into memory, it might be very different from what was on disk, thus invalidating the signature. So to achieve BPF program signing, kernel needs to do more. And there were a couple of approaches to this. Most of these were discarded, or the first two. First was trying to move the whole libbpf into the kernel, and that didn't work because it's big and unwieldy. Then there was an idea to implement a new file format that would be understood by the kernel, which was dropped in favor of new BPF program type, which probably was easier to get into mainline. So to understand what kernel needs to do, we need to understand what libbpf does. Its processes can be split into 4 main phases, but only the first 2 are important in terms of program signing. The open phase is where the object file is parsed and where libbpf learns about programs, maps, external functions, and so on. And the second phase is where the code changes actually occur. Here, libbpf probes kernel features, applies relocations, creates maps, and so on. Everything needs to be done by the kernel. One of the places where code changes occur is map creation. Before this change, BPF programs accessed maps through map file descriptors, but those could only be determined on load when the maps are created. So instead of referencing them directly, another layer of abstraction was added, which is file descriptor arrays. So now BPF programs reference indexes in these arrays, and the arrays are populated during program load. Another introduction is loader programs. So you might know that everything BPF related in kernel is done through a single sysbpf syscall. The first argument is is a command ID, and there's like 32 of them. So everything, map creation, program loading, attaching, BDF lookups, everything is done through this syscall. And the net result of libbpf is a list of these syscalls. The idea was to write those down and play them back when the time comes. And to do that, a new BPF program type was introduced, which could only call this sysbpf, syscall, and also sysclose, and could only be ran from user context. But it's still a BPF program, and we still need to load it. That's where light skeletons come in. The normal workflow with libbpf is that you create some BPF programs, put it in a C file, compile it, get an object file. That object file then gets parsed by BPF tool, and you get a skeleton header file. That skeleton header file contains the whole original ELF object file, and it also contains structures describing maps and programs and so on, and it also contains multiple functions to work with those, to load, attach, and so on. And then you take that header file, include it in your user space program, and work with it through this. The light skeleton is different in that it does not contain the original ELF file. Instead, it includes the loader program. That also means that we don't need libbpf or libelf headers anymore. So your user space program would not depend on those. For your user space program, the change is almost invisible because they're interchangeable. The only thing is you cannot use libbpf functions anymore. And in most cases, that means that you'll need to change the way you access map and program file descriptors, because usually they access through libbpf functions. Now you access them through the skeleton structure. All of this was just one single page set, but it still missed a couple of important things. One is core support. It is very important because it allows for greater BPF portability. In this case, the full source file that implemented it was changed so that it could be compiled for both kernel and user space. And this allowed to get more BPF programs through light skeleton and allowed to remove libbpf dependency from BPF preload UMD. BPF preload is a number of BPF programs that are bundled with the kernel. This also enables languages such as Go to use the full advantages of core. Before that, they couldn't because they can't adopt libbpf for whatever reason. And the last thing is light skeleton in the kernel. So instead of including light skeleton in your user space program, you can include it in kernel now. And this allowed to drop user mode driver from BPF preload completely. And that means now we have BPF code in a kernel module, which can be signed. So we get BPF signed code. Well, only kind of. Because it's a module, it lacks portability, and so we are still away from true BPF signing. But I hope next time we talk about this, it will be there. That's it from my part. So, questions? Yep. Yep.
I have one. What's the best source of information for BPF nowadays, except for mailing-list archives?
Well, kernel documentation, I think. Kernel documentation, actually, one of the important parts that we missed. The question was, what is the best source of information about BPF? Important parts we missed. During this last year, a lot of commits were devoted to documentation. So documentation directory in kernel is very good now.
And there's also two books, with BPF main author as well. It's also a good source of information.
Yeah, so there are also books on this by the authors. Yeah, the latest greatest is kernel source tree. Go there. And self-test directory. Yep.
Yes. In the BPF tree, there's
K-props and
Can you repeat the question?
What's the difference between K-props and K-functions?
Oh yeah, So you're speaking about BPF trace tool specifically, right? So the K-probes are the standard. They depend on which kernel mechanism they use to attach to the functions. K-probes use the K-probe mechanism, which has been in kernel for a while, while the K-funcs, which are unfortunately named the same as the K-funcs in kernel, but they are a different thing. So the K-funcs in BPF trace map to F-entry, F-exit probe types or program types in BPF, which are special BPF special probes that allow you to attach to the beginning or to the end of a function. They are much quicker than K-probes. They have some more advantages such as access to function arguments and so on because they leverage on the BPF type information, BTF.
Regarding the BPF loop construct you showed before,
yeah.
It looks like that introduce an indirect call per loop iteration, and indirect calls in the kernel are sort of bad from performance perspective due to like line and flip. Does BPF do anything to avoid the indirect call? Which are the performance impact of that indirect call?
Yeah. So the question was the BPF loop helper introduces an indirect call, which is generally viewed as a not very good thing in the kernel because it can introduce many problems. And the question was if BPF is doing something to mitigate those, if I got it correctly.
Specifically from performance perspective.
Yeah, specifically for a performance perspective. To be honest, I don't know. I don't have that much insight into this to know. I guess yes. I expect that that they are employing some mechanisms, but I don't know of any particular one. Sorry.
Do you guys have like any stack depth constraints inside the BPF for deploying programs? Like
What constraints?
if you guys like if there is any control how deep the stacks are going through the node of the BPF programs, or if there are actually any limits like the current so if it's stack depth.
Stack depth. Yeah, I think so.
Yeah, so the question is if there are any limits to stack depth in BPF programs. Am I correct?
Probably there is. I just don't know how you guys do this.
There is. So one of the things is that the BPF stack is quite limited. It's like 512 bytes in total. And I don't know the exact limit, but there is a limit on the stack depth that you can have. It's checked by the verifier. The limits in general are quite strict in the verifier, often more strict than developers would want them to be. So the question is, since BPF acts sort of like a virtual machine inside the kernel, what is the overhead of executing BPF programs? And specifically with tracing, what is the difference using BPF programs for tracing than kernel tracing? So basically, it's called a VM, and the programs are called that they are just-in-time compiled by, but basically there's the translation from BPF instructions into native instructions is usually one-to-one. I would say. So the overhead is just basically looking into a table which tells you which instruction to convert it to for the specific architecture. So the overhead is like very, very close to zero. Okay, and we're out of time. So thank you for the attention. Thank you for coming. If you have any other questions, just feel free to grab us on the corridors and discuss more. Thank you.
Now everyone is ready. We are tracing the Linux network in state 20.
Okay. Thank you very much. Sorry for the delay. My name is Adrian Moreno, and I work for Red Hat for the networking team. And I'm here today to present a new tool that I have written with my two colleagues, Antoine Tenard and Paolo Valerio. We're going to talk about networking and debugging and tracing. So this is a short agenda. I will try to go fast through the slides and run a live demo, although given the situation, I don't know if I should just anyway, let's just jump directly to the problem. The problem that we're trying to solve is network visibility and network tracing. And at least for me, this is a three-dimensional problem, meaning we have, on the one hand, we have many components in the Linux kernel. So we can have a packet in the TCP stack, UDP stack, TC, net filter. We can have it in OVS. OVS is especially complicated because the packet temporarily goes to user space and then it gets re-injected into the kernel. So there are many places where a packet can be. But on each of those places, we not only have the packets that we want to look to, we have all sorts of packets. So our traffic is hidden among lots of other packets. So we need good filtering. But apart from that, the packets mutate over time. So filters get stale. You can filter on the source IP address, and then the source IP address might change because you do something like nothing. So it's really complicated. You have these three dimensions to try to find your packets and know where they are and what happened to them in the kernel. So looking at the existing tools, we have, of course, venerable TCP dump. We all love the PCAP filtering. You can express any filter and it just works. It's like, and it is, of course, the seed of eBPF, so our respects. We have other tools like DropWatch, which is just focused on drops. It gives you the stack trace of each drop. It's really nice. We have PWRU. If there's someone that hasn't tried this tool, I recommend you to use it. It's awesome. It probes many different places. And we also have tools like BPF trace, perf, system tap, which are slightly complicated, to say the least, but very, very powerful. So with all this, what is Redis and what is the tool that we've written? We can give a definition. It's a tracing tool that gives contextual information of different places in the stack. But you can also think of it as TCP dump plus PWRU plus perf times Rust. Of course, we haven't put all the features of these tools into ours, but we do have we have gotten a lot of inspiration, lots of nice things that we like from these tools. We have kind of integrated them. So if you do know these tools, you might feel that something sounds familiar. So let's just jump into how to use Redis and try to understand this tool. And for us to understand this tool, we just can jump into an example. This is an example of Redis and the output that it just prints. Okay? So if we understand this, we understand Redis and what it does. So first of all, Redis is based, it has something that we call collectors. Collectors tell Redis what data to extract. So for instance, we have the SKB collector there, and the SKB collector collected information from the SK buff, from the packet. So that line, which resembles TCP dump output, is what the SKB collector generated. We also have the NFT collector there. The NFT collector generated that little line down there, which is NF tables chain, verdict, and table. So collectors collect data and extract information from the kernel. And on the other hand, we have something called probes. Probes tell Redis where to look for packets. Some of the probes can be explicit. So in this case, we have over there an explicit probe. So we told Redis, please get into the kprobe IP RCV, which is a well-known function in the IP stack. And therefore, that probe was, that kprobe was probed. Basically, we attached an eBPF program there, and collectors collected the available information. So some of them are explicit, but some of them are automatic. Like, for instance, the NFT collector. The NFT collector, you cannot just collect net filter, like NF table information from anywhere in the kernel. So it automatically added that probe in a special place in the kernel where this information is available. So we have probes and collectors, and if we start combining them, we try to, we think we're able to achieve a fairly good low-level tool for network tracing. We have many existing collectors. I'm going to just quickly go through these slides because we don't have much time because of the delay at the beginning. We have the SKB collector, collects packet information. We have the NFT collector, which also we shown in the first example. You can filter, it can do something really cool, which is filter on the verdict of the net filter rule. We have SKB drop, extracts drop reasons from a special function in the kernel. We have SKB tracking, because we do extensive tracking of packets. So that is a very important feature inside Redis. We have an OVS collector. So just a small reminder of how OVS works for those of you that might not be familiar. In OVS, we have a kernel data path, but it acts like a cache. So it's empty at the beginning, and the first time we see a packet, we send it to a user space daemon, where we process it and we determine what to do with it. And then we put the packet back into the kernel alongside a flow that tells the kernel data path what to do with similar packets. So then the next packet, which looks similar, will be just processing the kernel data path. So we have an OVS collector which does exactly that. Traces, adds some automatic probes in the kernel data path and the user space daemon in order to extract all this information. This is a short summary table of these collectors. And we found a problem, which is, as we start adding probes, since they are explicit, like many of them are explicit, we end up having very long command lines. And we need kernel knowledge to actually know what to probe, right? So these might be obvious for a kernel networking engineer, but might not be obvious for the rest. So we developed something called profiles. So it's just a YAML file where we list the probes, we enable the collectors, and it's very simple, easy to share, easy to ship in your distro packets or whatever, easy to write one for specific use cases. and have it ready for your debugging sessions. So you just enable the profile, and that's it. And one of my favorite features, we have pickup filtering. So same syntax as TCP dump, exactly the same. If it works in TCP dump, it will most likely work in Redis. It's like 99%. I think like for most common use cases, it will work. Yeah, Redis gets that, translates it to BPF, translates BPF to eBPF, and inserts it into a kernel for filtering. And similar to perf a little bit, events can be stored in files, and for easy post-processing. And events, in this case, are just JSON. So you can do any kind of post-processing. You can write your own post-processing in Python or whatever, and get some more insights from your events. We have one of the built-in post-processors is the sort event, the sort command, which I will show you in a live demo, actually. So fingers crossed, bear with me. So this is a very challenging. Okay, so sorry, I had to reboot the machine just seconds before starting, so I hope my script works. Okay, so I have a very simple setup here. So we have two network devices attached to two network namespaces, a private one and a public one, and we're just NATing, like masquerading between them, okay? So, for instance, if I'm gonna enter the private network namespace, and I'm going to ping so I have connectivity with the public one. So I'm going to just also verify this. So this is I'm pinging this IP address, right? And okay, I have it cached. Okay, so I'm going to capture the packet as it's received, and as you can see, the source IP address is not the source IP address that I have here. So there is nothing going on, okay? So let's see how Redis can let me keep that ping flowing. And I have some profiles installed. So I have a UDP profile. I have also a generic profile, NFT profile. The generic profile is shipped with Redis, and it's with V1 at least, and it's a generic, pretty useful for starting a debugging session. So I'm going to use the generic profile and the NFT one, right? And I'm going to collect. I'm going to filter on host 192.168.102. Okay, so that's interesting. Okay. So live demo, of course, is not working. Why is not, okay, sorry. So, sorry for that. I have a plan B, which is I have a, oh gosh, but this is not visible, is it? Do we see something there? Oh my God, sorry guys. So, can we do like zoom in? Yeah, I just rebooted this machine before, and do you guys see something? Well, these are events, okay? So I just run the NFT, collector, and this printed a bunch of events, right? What I wanted to show you is this is just putting some events into a file called events.json. Okay, so events are stored in a file, and after that, I can run the short command. When I type short events.json, ready short events.json, this is the output. So as you can see here, at least visually, I hope you can see that most of the events are indented. This is because we detected the first packet, and we identified that the rest of the events belong to the same packet. And we identify that even through NATing. So at some point, the source IP address of the events changed from here, which is 192.168.102, and it become another one, right? So basically, with this demo, I wanted to demonstrate that we can get events all around the network stack. So IP receive, we get the IP forwarding, we get NATing, we get NAT manipulate functions. We see the NATing going on, and we see the packet being received. Later on in this demo, I increased the rate of the ping, and I see that some packets are being dropped. So doing the same experiment, like collecting the events and sorting them, I can look at the drop, and I can see how, maybe you don't see it, but at some point you see a drop in the NF table, an NFT event dropping the packet, which has a different source IP address than the one I put in the filter. So even though I was filtering on the source IP address and the source IP address changed, I was able to detect that and detect that that packet, specifically that one, got dropped because I had a net filter rule in egress which dropped it. And at the end, I see this SKB drop event with the SKB drop event reason, which is in this case is net filter drop. Also, there's another way to see it. There's we can enable just the NFT, just the SKB drop and the NFT collectors, and put the option ---- stack. The ---- stack will print the stack trace of each event. So we will capture the events as they get, the packets as they get dropped, and print the stack trace. This is similar to DropWatch if you know the tool. Okay. And here, again, pretty small, I think. Sorry about that. So in this other demo, I have Open vSwitch setup. And in the Open vSwitch setup, just two namespaces communicating each other through OVS. And in this particular example, I use UDP, a DNS resolution. So I run a DNS server on one side and a DNS client, basically a DIG, on the other side. This is what I was telling you about. So this is the cache, the content of the flow cache. Okay, the first time we see a packet flowing, two entries appear, two flows appear in the kernel cache. For any other UDP packet will hit that flow and directly be output to the right port. And after a while, the cache entry gets invalidated, expires, and gets flushed. So in this particular example, what we see is, of course, we have a profile that helps in this use case. The profile defines some traces in the UDP stack and some traces in the OVS stack. Profiles can be combined with each other. So in this case, we have two completely independent, self-contained profiles that, when combined, will help us debug this particular case, in which maybe we have some latency in UDP resolutions. So we start collecting, we execute the example, we stop collecting, and we run again the sort command. And here, the sort command gives us a very big a path of events that belong to the same packet. Okay, and of course, it's not very visible here, but at some point, so we see packets in the vEth port of the source network namespace. We see the event. We see the SKB going from one network namespace to another, because we list also the network namespace in which we see the packet. We see it being received by OVS. We see it being processed by OVS. We see it being upcalled by OVS to user space. We see it being received by OVS in user space. So we know that it wasn't dropped in the middle, like we didn't overflow the netlink socket that we use. We then saw a flow being put, like a flow being configured because of this packet. And we saw a flow being executed, meaning the packet being re-injected into the kernel. And then we see events where the kernel receives the packet and executes an action, which in this case is an output action to port whatever. And then the next event here is vEth transmit, again goes back to the vEth and up the IP stack and the UDP stack of the DNS server. So we see the entire flow even in user space. Of course, if we scroll down to the next event, okay, so if we scroll down to the next event, what we see is the next packet didn't go through user space, and we see OVS DP execute action right after it being received by OVS, meaning we are able to see which packets go to user space, which packets stay in the kernel, and we can see drops or any unexpected behavior with packets even in user space. Okay. Yeah, I'm really sorry I couldn't do this live, but you know. So I can show it here a little bit bigger. So this is the output of the sort command. You You see the first line is the first time we see the packet. Oh, sorry, let me. Well, anyway, the first line is the first time we see the packet. We see here in the IP RCV, and then we see NF contract, ICMP, NATing going on, right? So we see all the events sorted. It's like TCP dumping everywhere in the kernel and being able to see it in a nice sorted manner. What's next? We have just released the first version. We have many collectors planned. We want to add contract, TC, container integration. We want an embedded Python integration, terminal user interface, and whatever people suggest, right? So contributions are welcome. That's the GitHub repo, and you can just create an issue and suggest profiles and any other feature that you would like us to work on. And that's it. Sorry the demo didn't work. Last minute issues as always. And that's it. If there are any questions, I'm Yes, Paolo. So there are different techniques. So inside the kernel, we trace the SKB. The first time we use the SKB head, and we track whenever the data pointer changes, so we know when it mutates. But essentially, we use pointers inside the SKB to track when the event belongs to that same SKB. When we in OVS, we don't have a very good infrastructure for tracing packets from the kernel to user space. So then what we do is we get hash from different parts of the packet, because we don't have an SKB struct in OVS. We just have the bytes, right? So we hash it. We use other techniques to track the packet through OVS, because there are several places where OVS installs flows and does things like that. And then we also hash the packet when OVS reinjects the packet into the kernel. So that's how and then we kind of combine both tracking information into a single one for us to be able to sort all those events. Yeah.
So on top of this, what you just said, with tracing and using different stuff, then you jump into user space. So is there a combination of many different parameters would make you lose track of this packet? Because okay, in kernel you can trace it effectively at any point in time. So whatever I mutate in the packet, you will be able to always trace this particular packet. But if I do jump to user space, could I modify in user space, let's say, source IP, destination, source port, destination port at the same time, and then you just lost track because you hash with the assumption that some parameter will always stay the same, and then when you take it in user space and you say, I lost the track.
Yeah.
Or not possible because of the way how it is done.
I don't think we can trace any user space application that can change the packet in any way. Like, we cannot do it in a generic way. That's what I mean. We can do it in OVS, because we know how OVS works. I happen to work in the OVS team. So we use OVS internal knowledge to know what OVS does and to the packet. In addition to that, we expose user-defined trace points in user statically defined trace points, USDT, So we allow in OVS in user space. So OVS has hooks for eBPF programs to be run. So this allows us to extract that information in very specific key places. Of course, not all applications might do that, and each, let's say, each data path or control path that we want to monitor, we would need a specific collector that knows how to do that. So yeah, I'm hoping that we can add or other user space applications, like other control planes, other programs that alter and modify the behavior of packets, but yeah, not in a generic way. Yeah. No, we don't have a user interface at the moment. We just have the CLI. We would like to add a terminal user interface similar to what Perf has, where you can have all the events, inspect them, expand these little tables, and collapse them, filter, and things like that. So we want a terminal user interface, but yeah, it's just in the backlog. Yeah, go ahead. Yes? Yes. Yeah, it's. Oh, okay.
You also need to repeat the question.
Oh, sorry. So, okay, so the question was, how do we do how do we convert the pickup filter into eBPF? Yes, we do use lib_pickup to convert it to legacy BPF, and then we basically manually convert instructions from BPF to eBPF. They are mostly a one-to-one relationship, but not exactly. And so we create an eBPF program that has that functionality, that filter, and we attach it to the rest of our eBPF programs. So it's pretty cool, actually. Okay, thank you.
Right, so the talk is already introduced. I can skip the part and save 20 seconds. Well, I'm Stefano anyway, and
I'm Alice Frosi.
And right, so we are talking about Satan, but that's not the thing you eat. We are actually talking about a lot of privileged operations in the sense of system calls mostly, seccomp, containers, virtual machines. Some problems about them, or what we think is a problem in terms of security, and the solution we propose. After that, there will be a demo, and then questions, and don't overestimate us, but we hope to answer to your satisfaction. So quick recall, or what do we understand as a system call. So in essentially every modern operating system, you have several rings, right? So you have a kernel ring, you have a use space ring. That might be ring 1 or ring 4, or in any case, you have something like a system call abstraction. In case of Linux, it's simply that you have a process requesting resources or services from the kernel. And this is, maybe perhaps the main security model that an operating system implements. So depending on your user or capabilities on Linux or context on Linux and BSDs, you might get that this request is granted or denied. So if you ever try to insert the famous module that's called evil things as a user, the kernel will not let you do it. However, if you touch your own files, then the system call will succeed. And the difference is just that, well, the number of the syscall is different, and root could do this, and root could also do that. Okay, that's kind of obvious, but useful maybe to introduce what we want to improve. So quite often we see in container environments and virtualization engines or mixes thereof, such as, let's say, KubeVirt or Kata containers, for example, but even if you just stick to Podman and Docker. Let's say the container wants to create a network interface. That's usually a TUN. It's like the most basic tunnel interface on Linux. And you need to do it the old way. So without netlink, you have a IO control, and you want to, tell the operating system, I want to create a network interface. And on Linux, this doesn't need root anymore, but it needs capnet admin, which means you can do pretty much whatever you want. And you can create how many interfaces as you want, spoof the traffic, bring down the networking. So there are a few other examples of these things that are actually quite common, like, for example, setting up the priority for a real-time virtual machine, where you just need to affect the priority of one process, not all of them. There are other problems right now. So, for example, you want to create a device node as a user. You want maybe to connect to a specific daemon or open a specific file. And all of them, there have been impressive improvements recently in Linux, but wouldn't it be nice if we could just say, okay, I want that this process can create this top device. And sure, Linux security modules do something almost like that, but those are kind of fixed policies. They're not so easy to dynamically configure them per process. So we started looking into it, and of course, BPF in seccomp is an important part of the story. You can do seccomp with a small BPF program where you say that you might want to deny or accept a syscall based on its number. Not good enough because that's still too generic. Big improvement again in Linux recently. You can tell another user space process details about your syscall. This is called seccomp_notify, and essentially, yeah, the kernel tells you a lot of things, arguments.
Transition time. Container already make use of seccomp. Usually, you have a JSON file that defines the syscall that are allowed, denied, or notifiable by the container. So usually the runtime take the seccomp profile that is part of the OCI spec, and basically it uses libseccomp library in order to use to generate the BPF filter, as we saw from what Stefano just described. BPF filter is needed for filter the syscalls. In OCI, we also have support for seccomp notifiers, and basically the runtime need to communicate with the monitoring process through Unisocket. So basically, this is the OCI extensions. So through this Unix socket, it passes a file descriptor where the monitor will receive these notification events. And when this starting phase is done, then the monitoring process is able to monitor the container and take action if one of the filter syscall is executed by the containerized workload. So there are already existing solutions that take advantage of seccomp notifiers, like, for example, LXD, or there is a King Vault seccomp agent. However, those projects have in common that they implement an handler per syscall. So, for example, if you want to add a new syscall, so maybe even changing the behavior, you need to code it yourself. So it's not very easy to reuse. In order to do that, of course, you need to have a deep understanding how seccomp notifier works. And this is the place where Satan comes to play. So the idea is that if you are an admin or you are developing a tool, you will be able to describe this into a recipe. So basically, you will have a match. So basically, this describes the syscall that you want to filter on arguments, and you will associate an action on it. So basically, this will be, we choose to use JSON format. And the Satan cooker is basically taking this as an input file and generate the BPF program, and then a bytecode representation of matches and action. We need a kind of launcher that installs the BPF filter in order, and then launch the real process that we want to monitor. And this is the goal of Satan Eater. So the actual monitor is what we call Satan. So basically, this take gluten, that's the bytecode representation for matches and action, monitor the notifiers, and then basically perform the action in behalf of your target. So here you have a visual representation of the flow. So we have two distinctive phases. We have the generation of inputs that can be on a completely different building system. So it doesn't need to be like we saw in the container runtime when we start the container. So cooker will read the recipe that you wrote, will generate gluten that will be the input for Satan, and the BPF filter that will be launched by the eater. So when the eater launches the target, then basically Satan can start monitoring the target process. So why Satan? So we decide to choose a declarative approach versus an imperative. So this gives you a better visibility of your operation, so the privilege operation. it's flexible, so you don't need to code an extra handler if you want another behavior. It's entire. The Satan setup will take care of that. So what you need to do is just writing the JSON recipe. It's a generic, so it's an independent and self-contained tool. We are not relying on libseccomp. We are going to see that in details, but basically this setup generates the BPF program and the matches and the action that we saw. So here you have a visual representation of a code. It's a snippet from KubeVirt, but you could solve it with the JSON recipe. So this actually, it's a nice representation what we mean declarative versus imperative. So, of course, security is one of the strongest and large use case that we have and saw about for Satan. Rootless container, so we want to target rootless container by reducing the number of capability given to them by impersonating only the necessary syscalls. A nice thing with seccomp is that you can have a deep argument introspection. So for example, you can check also complex objects such as, for example, strings, structs, and buffers. A nice add-ons that we think could be beneficial is also counting the number of the syscall execution. So again, this gives you a more fine-grained control of what your process is doing. However, security is not the only use case. We think also could be used in other contexts, like for example testing. So for example, you could inject some error if you execute a certain syscall. So for example, you want to simulate how your application behaves on different error. You can also mock a syscall, so not execute on your system that particular syscall, or maybe another thing could be injecting some delay, so simply a sleep and then continuing the syscall. We have a deep introspection of arguments, so that could be used for profiling your application. So for example, it could be an alternative to tracing tool that use ptrace today. We already mentioned, for example, could be also used for managing the resource allocation. Like, for example, seccomp allow you to inject file descriptor into the target process. So this could be an alternative way to SCM writes or the use of pdfticketft. Or maybe you could, a use case of could be to connect maybe to container, two applications that runs into the container that don't have the by mount, so the socket is not available to the both containers, so Satan could take the file descriptor of both applications and connect to them. So those are just some examples. Here, finally, you can see an example of the JSON that we were mentioning. So you can see that there are two sections. The first is the match. So in this case, we filter a make node with major number 1 and a subset of minor. So basically, we are going to do a privilege operation, so the call only for certain type of arguments. And the action that will be performed is basically redoing the make node in the context of the target. So you can see context mount caller. The second example is what I was explaining to you about testing. So in this case, we have a match on connect on two different paths. So you can see test 1 sock and test 2 sock. So if your application try to connect on test 1, we'll basically simulate the syscall because we return 0. And in the second case, we are returning an error, this -1. So these are just some JSON examples that you could describe with Satan. So now more technical details. Okay, sorry for the transition.
Right. The cooker generates two parts, right? We said There is a BPF program because we need to tell the kernel, please tell us about a number of syscalls, not all of them, otherwise we would have a few problems. I mean, that wouldn't be really useful if we just got all the calls, like IO calls, like read, write, or send message, or networking calls in general. So we need to be selective. We just want to get what we are interested in, and this is the role of the BPF in the kernel. So great. This is nothing new. No? You see a binary search tree. That's what libsecomp implements. Why do I have a binary search tree? Because, well, I have a list of syscalls, and maybe they are a bit more than 7. Maybe there are 200, and then every time BPF needs to check if it's a matching number, well, it's a comparison. So we want to keep it's actually quite relevant to keep a average complexity for the search operation to something reasonable. Okay, great. For that we have big O of log n, but there is something that makes libsecomp job a bit simpler than what Satan does, because libsecomp is used typically to just deny or accept syscalls. However, we need to be a bit more detailed, and we need to do like, accept, deny, or notify. So we have 2 optimization goals. And one thing that we found to be quite effective in our solution is to fill the bottommost level, the leaves, with some intermediate, more jumps. Like there are redundant jumps to these possible actions that are, sure, here we just show the user notification, or let the process do it as if nothing happened, or block it. Then, right, and this brings me to what's the overhead, you might wonder. We haven't been really scientific yet, because, that would need a bit more time. But essentially, what we did is to try and run 10 million LSIC on a postmodern 10-ish years old something laptop. And well, the Linux got quite fast, or maybe CPUs got quite fast, or something got really fast, I don't know, but it just takes 7 seconds. Okay, so we tried a typical usage of BPF that we see with Satan, with filters that might make sense for typical Podman containers that need to just mount a volume. So it's 100 instructions that do essentially nothing, plus we have some comparison, and then we jump across this filter. And that takes a bit longer, 8.2 seconds. But from there, we estimated that every comparison is something between 20 and 40 clock per instruction. Again, there might be something better on the market now. So I guess we don't care, or we do, but this should show that what we're doing is actually doable. Now, we were talking about the BPF, and this is the other part. So this is the part that is digested, sorry, for pun not intended actually, consumed, same, by the user space monitor. So the user space monitor gets notifications, and now it needs to decide what to do with it. So this is pretty generic. I'm sorry how obvious this is, but we have an area of instructions, an area which is read-only with the constants that you put in the JSON. We have a temporaries area. That's the only read-write part. And that's pretty much it. And we have a structure that's really simple. That's what seccomp gives us, which is a list of the arguments plus the PID of the target. And looking into instructions, we try to keep them to a minimum. And we are, of course, concerned about feature creep. But we are quite committed to not add more than this, because otherwise, what we are doing is we will not really be able to claim it's secure, and it will not actually be secure. So the options are, well, the obvious one, okay, check that the syscall number is matching what I wrote in the configuration. A couple of them are specific to seccomp. So seccomp allows us to inject a file descriptor atomically, so atomically with a call, meaning that the task cannot do anything else. Meanwhile, and this is useful if you, well, you see it later in the demo, but you can connect to something, and the supervisor connects you to something else and replaces the file descriptor. And this is actually safe to do. We can return an error or success, and then we need to shuffle a bit the data around because, yeah, the configuration comes from JSON, and the process can pass whatever in it. And a quick mention about the context. So by context, we generally mean namespaces on Linux. We also enable specifying the namespace, the several types of namespaces where we want to execute a syscall. So when we impersonate a syscall, we want to be able to, for example, yeah, for a container to do that in its mount namespace. And plus, yeah, obvious boring things such as a working directory, UID, GID. Tags, so in this JSON recipe, of course, we need to have references between matches and actions because we might want to recycle some data. Security, how bad is security with this? So it looks like we kind of explained to you a rootkit so far. But that's not our intention. And actually, what turns out from a bit of experience we had with yeah, several container engines or virtualization, no virtualization in the sense of a VM, because yeah, in that case, you know, you have a much stronger isolation, and you wouldn't need to use this at all probably. But let's say you have something in between or a mix. And yeah, sometimes you need to, I mean, we look at it and we think, okay, yeah, actually, I didn't want to tell a component that an RPC needs to pass a path about a file that I want to open. What you need to do is to open the file, and maybe there is actually a way. So the obvious benefit of this is, yeah, that instead of implementing several types of RPCs that we saw in several projects, you can have a unified mechanism. And unified both in the sense that this should be generic enough to be used by different projects, and also that for the same container or the same engine, you can have a single place where you just say, okay, those are my set of privileged operations and nothing else. We don't want to do the parsing in the supervisors, of course. Right now it's 500 lines of code, and we really hope to keep it that way. There is a surface, definitely. There is a significant attack surface, and in that link, we listed a few considerations about those, but overall, we think it's not perfect. It doesn't guarantee security by itself. It's not magic, but we think there is some clear value in this solution.
Okay, so now we have a live demo. We have a website where you can find also all those demos. So if something goes wrong, please go there. Okay, so we have seen some example. Now we can see Satan setup in action. So first of all, I would like to show you what we are going to execute. So this is similar to the example I listed in the slide. So there are different matches. In the first one, we are going to try to connect to a different path. So you can see that in the match we have a cool sock, and we're going to try to modify the connect and try to connect to the demo sock. So different paths, different server, and in the second match we're going to inject some error, permission denied, when we execute the connect, and in the third one is to execute the rest of the connect. So first of all, we need to generate the input file. So this is done by Cooker, that it takes as input the recipe. Then we need to generate the gluten, that's the input for seitan, and the BPF filter. Okay, so some prints, but we have generated the file. So what we would like to do is just to print to read some file and print it in the server. So I'm just generating a file that will be read, and then we can start the socket as a listening server. And this will be the path where we want to actually connect with. Okay, then we need seitan eater in order to launch our application. And this takes as input the BPF filter. And our application, it's again socket that is going to open the file that I wrote previously. And we want to connect to the cool socket. So actually we don't have this cool socket, but we try to connect to the server down. So seitan eater is blocking because it's waiting. There is some synchronization because we need to start seitan, otherwise we might lose some syscall. So seitan takes as input the other file that we create before, that's the gluten, and it takes the PID of the eater. Okay, I hope I haven't missed time. Okay, of course I did something wrong. You see what I did wrong. Okay, let's try again. Live debugging as always.
I didn't start this.
Okay, we didn't start the other socket, so let's do it again. I mean, it's live, so that's it. Okay, so now you can see that this has finished, and we have printed the string. Okay, the second part of the demo, we can kill this. We are going to try to execute the same command, but on a different path. So the different path, on this path we are going to inject an error. So seitan is always the same, it takes the same gluten files, and you can see that we have got a permission denied. So this can be a nice way how you can test on different behavior for your application. Of course, if you are going to do another path, in our case we don't have this socket, this connect is not filtered and it will be simply continued. In this case it fades because we don't have it. So those are the 3 matches that we had in the JSON. Okay, so this is the first demo. The second one, we are going to use Podman and try to create a character device. So here you can see that in the match we have make nodes, major one, and a subset of minor. And as a call, we are going to replicate the make node in the context of the caller. Okay, so first of all, I want just to show you what happens if we don't use seitan. So in this case, I'm just trying I drop all the capability here. So I'm not going to have cap make node inside the container. It's a Fedora. It's try just to create make node dev lol with some So yeah, I got the permission denied because the container doesn't have the capability. So now we can try to do to start Satan. So it takes in this, it's a slightly different flavor of, I haven't generated, sorry. So first of all, of course, we need to generate the input file, otherwise it's not going to work. Again, this takes the JSON file I showed you previously. Again, it creates gluten and the BPF filter. Okay, so now I'm going to start Satan, need root in order to be able to create a make node, the device nodes. So it takes as input again the gluten that we generate now. But in this case, we are not passing the PID, but a path to a socket. This was the thing I mentioned for the OCI integration for a second filter. So it's going to be okay. So now I will start again the same container, but I have added two annotations. So I hope you can see it. So in the first annotation, I'm reading. Can read. Yeah, so in the first annotation, it's second BPF data. And basically, we are reading the BPF filter that we generate with Cooker. And the second annotation is the OCI support for the second notifier, and it takes the path of the socket where the runtime will pass the file descriptor. Okay, and then we are basically as a command create again try to create the character device and try to list it. So we will see if it's successful. Okay. So you can see that now we have been able to create the character device because the call was actually performed by Satan. So in this case, we have been able to even create a character device without make node capability inside the container. Okay, so sorry. So the takeaway of this presentation are that Satan is a tool for filtering and executing privileges call. We aim to reduce the capability and the privilege given to containers. Important is the declarative approach versus the imperative way. And you can find more information into our website. Future plan are, of course, finish to code and a big cleanup. It's really needed. And yeah, right now we have very few syscalls, but we plan to add more. We would love to have feedback from you because it's a very new idea. So if you have any concern, please speak up. And yeah, our goal is to try to integrate Satan with container engines and virtualization engines such as KubeVirt. And special thanks to Andrea Arcangeli, Christian Brauner. His blog has been very helpful, and KubeVirt developers that help us to shape the design. So, any questions?
Oops.
Could you Sorry, I haven't realized it. Any questions?
So we have one question from the Matrix group.
Okay.
It's about the demo that we did with the make mode. The question is, you run this in all in containers. Is it possible to intercept and allow these kind of calls outside the container?
Yeah, I mean, the first demo.
Yeah, just repeat the question.
So the question is if it's possible to do MK node outside of a container.
Yeah, sure. I mean, the first the first example was without a container, and you could do exactly the same.
So the only thing is BPF program has to be loaded.
So yeah,
So does the BPF program need to be loaded?
Yeah, I mean, you have seen the two flavors of Satan. I mean, in the first example in the demo, we have used Satan Eater because it's exactly. I mean, we need to launch the process by installing previously the filter. Yeah, thanks. Thanks for your time.
We are out of time, so please ask questions outside or on Matrix and communicate on Matrix.
Hello, good afternoon. My name is Lukáš, and I would like to present a short talk on how we test a graphical user interface with OpenQA in Fedora. But this talk is not going to be an informative talk only. It should be an evangelizing talk, and maybe it could inspire you to start using OpenQA if sometimes you might look for something that can help you testing stuff in GUI. OpenQA is an automated test tool. It's mainly developed by SUSE, but we also use it in Fedora, and my colleague Adam Williamson helps developing it too. And OpenQA is fully integrated into Fedora. It's packaged for Fedora, so if you run Fedora, you can just install it in 15 minutes using the RPM packages. However, this talk is not going to be about installing OpenQA or setting it up. I talked about it last year on Fedora Hatch, and I'll probably talk about it again someday in the future doing a workshop, but this is just aimed on graphical user interface testing. OpenQA is good because it allows you to test various operating systems. So when I talk about Fedora, you could replace Fedora by anything. It could be RHEL, it could be OpenSUSE, it could be Windows. It's up to you what you put inside the virtual machine. Because OpenQA runs a virtual machine and performs the tests on the content of that virtual machine. Good thing also is that you don't have to install anything into the tested operating system. So you can just take the basic operating system, you don't need to add anything to it, you run it in a virtual machine, and you can work testing it. So it basically creates and runs a virtual machine. This can be based on an ISO file or a QCOW2 file, and you can perform various actions inside that virtual machine and evaluate the outcome. The architecture is that there is an OpenQA web application with a database that's a sort of a scheduler. You communicate with it using the browser or a REST API, and then it has a worker that performs all the jobs that it downloads from OS AutoInst. It has the tests, it runs VNC, and it uses QEMU to operate the virtual machine. The controller does the visualization, job handling, live viewing results, and it stores the results in the database, and the worker runs the tests and checks the needles and does all the other things that are needed to work with the virtual machines. You can have the worker and controller can be on one computer, so you can run it on a laptop, for example, but it also can be split, and you can run a scheduler or the controller on one computer, on one machine, and you can run workers on other machines, so you can have a bunch of workers and do multiple tests at the same time. Of course, you can do it on one machine too if you have enough RAM. The test itself is a Perl script, although it should be possible to write those tests in Python too. I have never tried because the test language, the test Perl is pretty easy, so it's just the basic Perl commands and some other commands from the OpenQA. And the test defines what you do inside of that virtual machine. So it mainly defines mouse and keyboard actions. and it checks and evaluates the needles. We are going to talk about the needles a little bit later, so you will know what that is. And it evaluates the expected, what you say you expect in the test script, so then you can compare it to what you get in the virtual machine. And of course, the test or the job can end with various statuses, such as passed, failed, soft failed, cancelled, and so on and so on and so on. The tests are Perl modules, and they are placed in the test directory. That's probably not that important, but if you see the OpenQA instance, so there is a tests directory with the test scripts, and there is also a lib directory where are the libraries with commands that you can use. And the routines we are going to talk about now are documented in the test API documentation, which is open.qa API test API. So you can check it there, because I'm not going to talk about it on a deep level. I will just show you what you can do and what routines you can use to test the graphical user interface, actually. Each test has a header where you define what libraries or what files, what packages it will use. You probably know, if you know Perl, so you know the use strict and maybe use warnings. These are useful things to do, because if you omit it, then Perl will not tell you about your own mistakes. So troubleshooting a test script is rather complicated then. And we say that we use the install test, and we use the test API library and the utils library in this header. In Fedora, these are mostly, the header is mostly standardized, and this is, I would say, a typical header for the majority of our graphical user interface tests. Then it should have a subroutine called run, where all commands must go. You can also use other subroutines in the test scripts, but then these are only visible in the scope of that module and not outside of it. So you can prepare some routines of your own. You can use it then in the run subroutine, but outside of the module only the subroutine run will be visible. And then it ends with the test flags. The test flags specify what to do when your test finishes, and by default all are off, so you can switch it on like this. For example, always rollback means that after the test finishes, it will return back to a saved status, because you can save the virtual machine on some point, then you can perform various activities, and after these activities are finished, you come back to the original state, which is great, which is a great thing to do when you want to start from the same point all the time. For example, if you have a graphical application and you start using your mouse and clicking on widgets, so you are moving the state of that application, and then, for example, you could start the next test, you could start at a certain point. For example, you open the help window in one test, because you want to test that the help window can be opened. So you open it, and then you do another test that uses another widget, but the help window is still opened. So you can design it like, yeah, you can do it like by design. I want to continue when the help window is opened. But then sometimes the test fails and the help window will not be opened. And it breaks the consecutive tests also. So therefore, it's good to start from a certain point, and you can save it, and then you can always roll back to it. Other possible flags are fatal, which means that if the test fails, then everything fails. Or milestone, which means that now, after the test, it's the point where you want to save the status of the virtual machine. And no rollback if you don't want rollback, or ignore failure if failures should be ignored. And then each Perl module must return a true return value. So right at the end, you have to place 1. This was when I started with OpenQA, I didn't know that. And I often would omit the 1. And then I was getting errors all the time, and I couldn't run it, and I didn't know why. And then I realized there must be the 1. Okay, so now you want to test a graphical user interface, which basically is you want to see something, you want to see some widgets, and you want to interact with those widgets using your mouse or using your keyboard. So OpenQA lets you do the following actions for the mouse control. You can set the mouse to a position, mouse set. This is good if you know to which position you want to set the mouse. Normally you would define the resolution of the screen in OpenQA, the resolution of the virtual machine, and you maybe know that the position of the widget is on 500, 600. So you could move the mouse to that position directly. Most of the time this is not the case, and I will show you how to fix it. You can hide the mouse cursor, move it out of the screen, because sometimes you don't want that cursor to affect the process of the test. You can click on the mouse, you can double click on the mouse, you can triple click on the mouse. Each of those commands, you can select the button to click, if it's the left, the middle, or the right button. How long it should be clicked, but I don't want to go that deep right now. And you could also do a mouse drag, which means you start on some point, you hold the mouse button and you drag to another position. Mouse scrolls are currently not supported. I visited the OpenSUSE booth this morning, and there were some nice guys doing OpenQA also, and I had a nice chat with them. And I asked about a problem that I have with a certain needle type, and then Defolos told me, and yes, but this is not such a big problem, but if somebody wanted to create a patch, it would be mouse scroll. So they also want mouse scrolls, we want mouse scrolls, but nobody has implemented it yet. And there is a workaround we are using in Fedora tests, and it's a keyboard workaround. So key events that you can use is you can send a key, which basically means press a key or press a combination of keys. Press and hold a key is a good point when, or good stuff when you want to interact with the mouse. So you can press and hold the key and press the mouse button and the release, both of them. That might be good for some sophisticated applications. Release a key, of course, is when you're pressing and holding it. So releasing a key releases the key. Send key until needle match basically is press the key repetitively until you find what you expect, which I am using when I need to scroll the mouse. So I am sending like a down arrow or a tab or something, and then the GUI scrolls. you can type a string. In Fedora, we have wrappers, type safely and type very safely, because you can specify in type string, you can specify how fast it should type and so on. And because we don't want to repeat it all the time, so type very safely types really slowly. Because when you just type a string, sometimes we were getting errors like it typed so quickly that it missed a letter, for example. Or it pressed the letter so quickly that it produced 3 consecutive letters, like instead of password, it produced PAAASWOORDDDDD, so this is not what you want. So therefore, we are typing very slowly with the type very safely command. Type password is similar, but it doesn't get logged in the log files, so that nobody should know about it. And enter a command is basically, again, type a string, but this time it adds a enter press at the end of the command. So you can have this one to run commands. And now we talk about needles that are a crucial part of the GUI testing, because how the test machine should know about what you want to see. And it's because you can compare a pre-created image with the content of the virtual machine. So you have a screenshot with an area defined that you expect to be found, and then OpenQA compares it with the content of the virtual machine, and if you get a match, it's good. If you don't, it's not that good unless you want it. So you have various, like assert screen means that you want to check that something is there. Maybe a widget is present or an icon is visible on the screen. Check screen is similar, but it doesn't fail if nothing is found, and instead it gives you an undefined value, so you can use some kind of diversions in your code, like if you find this, do that. If you don't, do something else. Assert screen and click is that if it's found, it clicks on it. Assert screen and declick is if it's found, then just make a double click. Then, for example, what we also use is click on last match, for example, if you have a check screen maybe, so then it finds a match and you don't have to write another assert, so you just use click on last match and it will pick up that last match and click on it. So you can say if check screen something, click on last match, and if not, do something else. And sometimes also it's very important to wait until a screen changes or to wait until the screen stays still, because sometimes OpenQA is pretty fast. It's much faster than a user is. So we had problems with KDE, for example, because KDE used sort of, how do you say that? Yeah, the word slipped my mind. Sort of animations, yes, that's the word. And those animations took some time, but OpenQA was so fast that it clicked somewhere even before the animation was ended and the test failed. So you say wait until the screen stays still and then it can do animations as it will, and the test waits for it and then finds the needle it should. There are some more. You can record a soft failure, you can record informations, and you can save a screenshot. However, it didn't work for me to save a screenshot. I don't know why, I must figure it out, but it should be there. You could also provide variables, either in the test setting or when you start those tests. You can you can define a variable, and then you can use the variable by get variable or set variable or check variable. So for example, you can say that in the test settings that you can say that the tag, for example, is GNOME, and then you can have one test script that could operate on GNOME and KDE, and it knows that the variable is set to GNOME and it will only do the GNOME part on that one particular run. And if you replace the variable when you start the script, then it will behave the opposite way and it will also only run the KDE parts. So what is the needle, how it looks like? So basically this is a screen with a graphical application, and this is the calculator, the GNOME calculator. And I took the screenshot from a real life test. So this is what we expect a user might see. But because it's so complicated when we compare the entire screen, so that there are so many problems, maybe like these little tiny dots, you know. We don't want to compare the entire screenshot, but we want to just compare if there is the button with the number 1. So from this screenshot, we define an area that the OpenQA should try to find, which is the button 1. And now it only looks for this particular part. Theoretically, this particular part could be found on any position of the screenshot. So it doesn't have to be just here. And if, for example, the graphical application is moved to the right part of the screen, it will still match. When we think about the needles, so it consists of 2 files. There is the PNG screenshot and a JSON description file. A needle must have at least 1 area. If it should be a clickable needle, then it should just have 1 area, and the click point lies in the middle of that area. The needle also needs a tag because it looks for them according to the tag, and you can have more needles with the same tag. The bigger the area, the more risk of mismatch, and you can also set the needle fuzziness that can be adjusted from 0 to 100, where with 0 it would be probably everything is a match, and with 100% is like a totally exact match is a match. So by default it's set to 96, and we sometimes go to 90. This is the JSON file. It looks like this. That's the tag to find the needle. And you know that there is the xpos, ipos, it's the coordinates, where to start, then width and height are the width and height of the area, and the type is match. That means it must find a graphical match, and the match fuzziness is 90. Okay, need for needles. Yeah, this is basically that sometimes you need to make more needles to cover for one tag because fonts differ, colors might differ, and stuff might differ. So for example, if you want to check the buttons on that calculator, you would need 24 needles, at least. The example, the test example, how you would click on those buttons and you would solve the 3 times bracket 3 plus 2 bracket closed equals sequence, you could solve with these commands. So it's basically assert and click, assert and click, assert and click, assert and click, and then compare the result, and that's it. And then delete it with escape, for example. And you see that this would require 8 needles do just this. So we have some more time, so I would like to show you the real test. This is a real calculator test that does various clicking and tries to do various examples or equations. It also shows the help. It also shows the about window. If you take a look on the code, it's slightly more complicated, but because we were trying to use a subroutine that does the calculation so that we don't have to repeat all the needles all the time. And the last thing I would like to show you is the video. I hope I can how can I make it slow? Speed, yes. So halve the speed, and so now it logs into the workstation. It starts the graphical application called calculator, and it shows the about. Now it clicks and solves the equations. So this is so designed that to solve those equations, it must click on all of the buttons. So we know that all of the buttons work, and we also know that the help worked. So this is a very short graphical test of GNOME calculator, and this is everything I wanted to show you today. It's so easy, you can start right away. I measured it, the installation and setting up the OpenQA takes 15 minutes.
When you know where.
Oh, okay. 30 minutes when you don't know. Okay, do you have questions? The good thing is, can I repeat the question? How do we test GNOME with Wayland or KDE with Wayland? The good point about OpenQA is that it doesn't care about Wayland at all. So it only compares the screens that the virtual machine is giving. So if it runs Wayland or Zork, it doesn't really matter.
But I saw VNC in that schema. Yeah, it's using VNC. It's VNC talking to QE. It's not VNC shared desktop.
Yeah. So you can test Wayland just fine.
You test Windows.
Yeah. You can test pretty much everything what can be run in a virtual machine. Pardon?
You can't mouse scroll, right? Yeah, you can't. You literally use the scroll wheel on a mouse, right?
You cannot do it because it's not implemented. Okay. So there is no way how you could tell the OpenQA now scroll the button.
Yeah, I think from my knowledge of Qmio, I think there may be one way to realize it. In Qmio, there is a QMT command named syndicate. It can send the various of the events of case. It includes the scroll up, scroll down. Maybe you can look at that and see how to use it in the framework.
Yeah, when I talked with the OpenSUSE guys, they told me that probably there is a routine which communicates to VNC and sends scrolls, but
So all your it's impossible to do. It just hasn't been done. The test API, which we're talking about here, is like the API you can use for testing, and it's just nobody's implemented mouse scroll. Nobody's gotten written the routine to set the correct VNC events and implement the mouse scroll. So it could be done, just nobody got around to it.
yeah. So you can't use it right now, but maybe we find some time and way how to do it. And
So all the communication with the guest is by VNC, right?
yeah.
Okay. It also uses serial console. So when you're running a script and asserting whether it passes or fails, it does that via the serial console. It redirects the output of the command over the serial console and then reads that and gets the return code out of it. So it's kind of like
If most of the communication is by VNC,
mostly VNC.
this feature cannot do that because for the send the key command, it uses the commute monitor. It's fancy big sockets and also okay.
Thank you.
I have an application which I would like to test using OpenQA. Can I actually add my test right with an add to this suite so that it runs on every new raw byte?
Yes. Yeah. If you want to, you can contact me anytime, and I could help you and show you how to do it. Yeah, of course. We have a repo where we store the tests. This OS auto-inst Fedora. It's on Pagure, and basically you see that there are the tests here. So in this we have applications, and each graphical application has a dedicated directory where you put all the tests you want to run. I think that it's useful to split the entire application into various tiny steps and start from the beginning again, always roll back, because then you know these tests passed, this test has failed, so let's just investigate more this one. If this is just one entire script and something fails in the beginning, then the rest doesn't get tested, never.
One more question regarding the applications. It is possible to install additional packages?
Yes, of course, no problem with that.
One more question. I'm interested in how mitigation is done via OpenQA, because I came from web UI testing, and we have XPath, allocators, and we understand right that in UI desktop you have only coordinates X and Y, and that's it.
Yes, but because we don't want to. Okay, do we have coordinates only to find the place to click, right? Yes and no. Basically, the engine operates on coordinates, but I would like to show this once more. So I could expect that the widget number 1 would be on maybe 800, 200 or something, which may be or may be not the case. So therefore, there is the needle system that you say that you want to look for this particular area, so a little bit gray with 1 on it, and OpenQA compares it with what it has in the virtual machine, and it will calculate the coordinates automatically, and it will click in the middle of that area. So it does, it calculates the coordinates for you. But if you want to specifically say it needs to be coordinate X and coordinate Y, then you use the mouse set and it moves the mouse to the exact coordinates. Okay, enough. Yeah, time's up. So thank you very much for your attention and have a great DevConf. Thank you.
All right. Okay, I think we're good to go. Hello, everyone. Welcome. Thank you for coming. And thank you to the organizers for letting me speak, giving me the slot. My name is Achilleas. I'm an engineer at Red Hat on the image builder team. And today I want to talk to you about how I'm not going to talk so much about how we build images, but how we think about defining and configuring the images and letting users sort of like invent the universe of image definitions, let's say. So one small thing I'd like to say, I don't know if this is a good idea, but I'm gonna be using a few, like some terms that we use internally, and with these things it's always a little hard to understand. I'm going to try and explain everything, of course, but it's always a little hard to know what other people are familiar with and what not. So if I use a term that's unfamiliar more than a couple of times, raise your hand and we'll see if we can keep the ball rolling so that I don't lose my audience. So yeah, let's get the show on the road. A quick overview of what I'm going to talk about. I gave you a little bit initially, but so we build images, and it turns out that building images is pretty easy, but making sure they boot and that they're useful is a tiny bit harder. So the trick is to sort of restrict users and the code itself, so that it's hard to build sort of invalid configurations or unusable things. But we also want to give users the power to sort of like explore the space of what kind of images you can build. And these two things are kind of in opposition to each other, right? So you can imagine a solution where you can only, like a project where you can only build 5 kinds of images or even 1. That would be really easy to test. You can't do anything else except build that 1 image. It always builds, it always boots, it's fine. It's just not a very useful project. On the other hand, you can imagine a situation where you can build almost anything, but most configurations wouldn't work. So we kind of need to find the sweet spot there, or sort of guide users and ourselves to only build things that make sense, but also be powerful enough so that it's useful. And so what I want to talk about is our solution, or like our way of thinking, where we sort of define abstractions about how we define images as configurations of components. And these components inform both the way we implement things in code, the way we define our own sort of libraries, but also how we want to present these configurations to the user so that they know what we're doing. So part 1, let's have a look at Image Builder. Image Builder builds images. And let's have a look at like the first, give a bit of an overview about what it looks like to use it. And I'll talk a bit about, like I said, how we build images, but most of the talk is about how we define them and how we think about what an image type is or an image configuration is. This is Image Builder. This is what it looks like when you want to build an image. This is Image Builder running on console redhat.com. And this screen shows sort of the first step of the image building wizard. This is where the user sort of selects a target platform, which defines the kind of image that we're going to build. In this case, you can see Amazon Web Services is selected, so we're going to build an AMI type image and make sure it works with Amazon Web Services. By the way, Image Builder also works on premises. We have it's not just a Red Hat product, but it's also a utility you can run on your laptop and build images from the command line, or from Cockpit Composer, or yeah. So this is like a follow-up step, sort of like halfway through the image creation process, where users can sort of select additional packages to add to their image. In this case, the user selected Nginx, so presumably maybe they want to run a web server. And what I'd like to do is sort of explain how these options and others like them, like selecting images or selecting the target platform, how they affect the process of creating the image and how we might be thinking about these configurations in the future. So at the core of Image Builder, like sort of like the bottom layer of our stack is OS Build. And OS Build is a command line utility that takes in a manifest and returns one or more file system trees. It does most of the work, well, it does the actual work of building the image. And a manifest is a giant, well, not giant, a rather big blob of JSON that describes a series of pipelines and steps. So you can see sort of here, like, there's an RPM stage, there's the kernel command line stage, hostname stage. So these are all steps that sort of modify a file system tree in very specific ways to create a file system tree that resembles a bootable image. OSBuild has, it's important to note, OSBuild has no knowledge of distributions or workloads or anything like that. It quite simply and very stupidly executes stages as described in this manifest and just returns whatever the result is at the end of the process. This is sort of a simplified look of what the JSON object looked like. I just pulled out the names of the pipelines and the stages. And you can sort of see that each pipeline is broken down into a series of stages. And most of these stages have pretty self-explanatory names. If it looks like the name of a shell script, that's probably what it's calling. So for example, the RPM stage installs RPM packages into a tree. The cloud init stage configures cloud init. Systemd enables services. You can configure the bootloader, install the bootloader, configure Nginx. And the nice thing about stages is that they define their inputs rather strictly, and they don't sort of expose the full, well, they don't always expose like the full sort of like breadth of what you can do with each thing, but they kind of, in a type-safe way, modify the tree to create a bootable image. And so, on its own, like I said, OSBuild doesn't really have any concept of what a distribution is or what it's actually doing in the grand scheme of things. So it isn't very useful on its own, and no one's expected to write manifests by hand or even understand the individual stages that we define. So we provide a library that holds the sort of like the domain knowledge of what a bootable image or a specific distribution looks like, and the library knows how to create a manifest that will accomplish that. And within this library, which we call OSBuild Composer, is where we define the base images that we present to the user, like the AWS image that we saw in the second slide. So again, following up, sort of repeating again what I'm trying to say here is that OSBuild makes no guarantees about what it's going to produce for any given manifest, in the sense that a manifest doesn't guarantee anything useful or bootable. OSBuild Composer, on the other hand, needs to produce images. Well, it needs to produce something that can be built and needs to match what the user expected, right? And ideally, it should be useful, usable. And the easy way to guarantee this, like I said in the beginning, is to restrict user choice. The smaller the configuration space, the fewer things that can go wrong. This is sort of what we have right now. So when we talk about image types, like the AWS image type, we refer to an image or an archive that contains an operating system tree. And it's sort of a predefined configuration that matches a distribution, a platform, and an environment, kind of like this, a three-tuple configuration. And additionally, the user can add their own little user customizations, like we saw in the example where the user can add Nginx to the image build. And these user customizations here are basically only the real, they're the only real control a user has to affect what what will come out at the end, to actually like apply their own preferences to what they want from the image. So for example, you can build a Fedora 38 image that can run on x86 in AWS, and then add an Nginx to the image. Or you can build something like a RHEL 9 image that runs on ARM in Azure, and add a 20 gigabyte OPT partition. And to repeat myself a bit, in code as well as the user interface, to an extent, it's these three first components that we use to sort of define the image types. And we do that in a rather static manner. So, for example, if we never explicitly added an image type that is called Fedora 38 on ARM on AWS, then that doesn't exist, essentially, in our code. So even though it's a perfectly valid configuration, we don't support it. It doesn't exist, as far as we're concerned. And so each choice of these each choice of these components, sort of the distribution, the platform, which is like the hardware architecture, and the environment it's going to run in, have very specific effects on the image building process. They're associated with different configurations of the stages we saw earlier to produce an image. So for example, the distribution sort of defines the base packages that you're going to need, and repositories that you're going to use to download them. And then the platform, again, specifies a specific subset of those repositories and some additional packages for like the bootloader or the firmware. And then the environment, which in our example was sort of the AWS, you add additional packages and configurations to make the image run in that environment. And so we would like to sort of move away from this sort of static configuration situation that I described earlier, where like everything's sort of defined as these static combinations of these three components, and towards defining the effects that the choices of these components have on the image building process. And if we can define, if we can have like a well-defined set of what these things do, then we can expand our configuration matrix to everything that's valid. And so this is the part of the talk where I describe where things that don't yet entirely exist. So this is sort of like where we're moving, where I imagine that we're moving with the project. And some things that might be more conceptual, for example, and might change in the near future. But what we want to do is define the choices we saw earlier as abstractions in our code, and then conceptually sort of, well, in our code, but also conceptually, and then help us sort of reason about what an image definition is and how we present these choices to the user. So we can go back to this sort of like breakdown of the components, where we have the distribution, the platform, and the environment, which before we sort of used in this sort of static way to define what an image type is, and then a workload, which sort of defines what the image is intended for. And so the distribution, as before, you can imagine, like I think we all know what a distribution is. So a platform, which is sort of which is the hardware architecture, but maybe a bit more generally, it could be a specific device as well. The environment, like we saw before, it could be a cloud environment like Amazon, Azure, or Google Cloud, or it could be a bare metal environment. And the workload, which again, like it's sort of the intent of what kind of work the operating system server will be running. And you can sort of think of the workload about the kinds of things that you would normally do at provisioning time. So installing packages, setting up configurations, and things like that. So we can sort of start selecting we can go through sort of an example of how selecting each one of these components, making a choice in each of these components, has an effect on what kind of stages we will be running and how it will affect the image building process itself. And so, for example, you pick a distribution like Fedora 38, and that sort of restricts the repository. Well, it selects the repositories, all the Fedora 38 repositories. So if you're going to build a Fedora 38 image, you need the Fedora 38 repositories. If all you know is that you're building a Fedora 38 image, you start off with the base package set, which is the core package group. And then if we're going to build this image, we need the Fedora 38 build environment. So that's all we have now. We only know that we're building Fedora 38, so this is what we start with. And then you add on top of that the option that you'd like an x86 image. So then you restrict the repositories to the x86 repositories. You don't need to be downloading anything else. And then on top of that, you need to add, for example, the bootloader packages for x86. And at the same time, you need the stages in the build process to configure and install the bootloader. And then at the next step in the environment, if you select you want it to run on AWS, it'd be good to have the cloud server package group and the cloud init, which is how images get sort of like provisioned or configured at first boot through the AWS Cloud Console. And since we're installing Cloud Init, then in the stages, we also enable the Cloud Init service using the systemd stage. And then finally, you might select a workload, like a web server, which would add an extra package, Nginx in this case. And then since we're adding Nginx, we also want to enable it and configure it. So that's an extra option on the systemd service, the systemd stage in the manifest. And then stage to configure Nginx. And so if the effect of each of these components on the image creation is well defined, we can sort of freely combine them. And we don't have to stay in this sort of like world of statically defined configurations. And instead of explicitly defining valid combinations, we can sort of restrict the configurations only to the things that we know are invalid, and then sort of like just let the space of known configurations exist. So we can sort of expose the entire configuration matrix in code to the user and know that any combination it would be possible. And so we're thinking now about what choices should we give users, and how can these choices map to the components that we're talking about here, the components that we defined. And so like the current state, like I said, is you have this sort of like static list of these triple configurations here, the distribution, the platform, and the environment. And then you give user a few knobs to sort of like add some packages or tweak some configurations. It's sort of these static configurations here are sort of exposed to the user, but not really. Like if you're on a system with of a given distribution, or if you're building for a specific distribution, then you're only limited to a handful of image types that we've already defined. And sort of the identity of the image is essentially this static configuration here, and then the user can sort of just tweak a few things. And our new setup, on the other hand, sort of puts equal weight on each of these components. So our question is, why don't we just expose all the components to the users, all the components, and sort of let them freely snap them together and create what they need? So what this would enable us is to sort of let both ourselves and the users define, just select, configure each of these sort of components. And what we do in turn is abstract away sort of the meaning of these components in terms of the image build process, but not the meaning of what's going to happen to the final image. So my question here, the reason I'm talking to you all about this today, is to basically ask you, does this sound like a good idea? At least this is how we're thinking about things, and like, is there something here that kind of, is there something that we missed? Is there a case that kind of wouldn't be covered by these configurations, by these components? Does it sound like a good idea to be able to just have an image like the one we saw, but instead of on AWS, you can just swap out the environment and have the same image for the same workload, just able to run on a different cloud service and be optimized for that cloud service. And that's pretty much it. Thank you. Questions and comments are, of course, welcome. And this is the website for our project and the GitHub repository for our organization. Question?
So I have a question about what is the motivation behind this project? I mean, assuming that we have a multi-material service, okay, and to decide to have, I mean, for me, let's say as part of the user experience, most probably we have predefined definitions according to, let's say, in the case of Redcap, with the Redcap folder. So you go there, you decide to use it, let's say, as a software as a service, and then you decide to export the images if it's going to be, let's say, for chef installation, it's going to be for some specific program. So you have it prepared without, getting any knowledge about how you're going to do it. So you get the curated image, and then you just simply run it. I have this kind of, let's say, motivation. But what was the motivation behind this project? I mean, what is the reason of this project?
All right, so the question was, what's the motivation in general? And I guess the extension to that was, how does it differ from if I'm getting like a base image and provisioning it and modifying it? Well, there's a couple of answers to that. First, well, someone needs to build the base image. So there's a lot of alternative projects that do exactly what you said, which is like get the base image. It's just like in our example, for example, it would be just get the base Fedora image and then add the bits to it to make it. So there's a couple of things that this project solves that I don't know, that we think is a good idea at least. First of all, every time you build an image, you get fresh content, right? If you're building an image today to deploy it today, you're going to get the up-to-date packages instead of maybe like needing to get an image that was built a week ago or a month ago and need to update it. You can. There's also the concept of like you're building an image for purpose, and it's well, there's a lot of things that are either impossible to, well, better to do or must be done at build time instead of provisioning time. For example, I think OpenSCAP is one. We have like hardened images. You can build a hardened image with certain configurations, and take an existing image, booting it, and then flipping those configurations isn't considered like compliant with certain security standards, for example. I'm sure there's a few other reasons and use cases. Everyone on the front row can probably answer your question in a different way. Partitioning, for example, is is another way. Like if you get an image, like we can partition during build time, create any partitions, almost any partitions the user wants, and if you just get an image and deploy it to AWS, you can add partitions after the fact, but it's certainly not, well. I guess like if you get a RHEL image and deploy it to, or a Fedora image and deploy it to AWS, you probably can't create a user partition after booting it, right? So there's a lot of reasons you want to configure something before you even build it.
I think you can inject some user data, so basically you can like customize it while you're like trying to run instance on AWS, for example, as you said.
Yeah.
So basically, what I'm trying to understand
Yes.
So you basically consume it, and let's say give or take, how much time does it take for like this page of definition you showed us before? How much time does it take to build it? If it's going to be for bare metal or Vimper or whatever, or Google Cloud?
So the follow-up question was, I guess it was the second part of the follow-up question was how long does it take to build and if it's provided as a service?
Exactly.
Yeah. So yes, it is provided as a service. It's on console Red Hat.com now for all Red Hat customers. And the image build time is, well, it depends on the image. It can be as low as, I guess, 5 minutes. Up to, I guess, 10 or 15 if you're building. And it's like the cloud images usually take like between 5 to 7 minutes. And we can also like deploy it for you directly to the cloud environment. We can also build ISOs, and those usually take a little longer.
So you can also import to the target provider, and basically you can put it on.
Yeah.
It's also the on-premise version, right? So you're not
Yes.
restricted.
Repeating that, there's also the on-premise version that you can run. If you have an RPM-based operating system, you can DNF install OS Build Composer and have it running and build your images now. I don't know who's first. You.
So you talked about having these defined component stages for environment workload types and whatever. How would that work in a model where you don't know what the kind of workload or environment somebody wants to use and they're trying to build on this using the tool?
Yeah.
Like I often encounter with image builds where people want to put together a set of packages, define a custom set of configuration and overlay some files into an image build at build time, because of course, as you said earlier, there's certain things you just can't do afterwards.
Yeah.
How do you do it with this model?
So,
Because so far I don't see a way that would work.
so the question was, how does this model work for situations where you might not know the workload, you just want to build an image? Well, first of all, the sort of like the workload situation is kind of optional. It doesn't need to be a predefined workload. The way it kind of works now, if we map this sort of like new way of thinking about things to the old way, we would of course have a custom workload or even a null workload where you don't get any extra packages, you don't get any extra configurations, you just get the base system. Obviously, you can't skip the selection of distribution and platform. That wouldn't make sense. Environment, you could have like a base environment that sort of it doesn't belong to any cloud or anything. It's kind of just something. I don't know. It's just something that can maybe you can have think of it as like the default is like a bare metal installation, for example. But that would totally be an option, right? It's like there's sane defaults, I think, for the environment and the workload that we can sort of think about. And
I'm also thinking of like when you're trying to layer in custom software.
Yeah.
Like, I don't know how custom software fits into this model.
Custom software, the follow-up question was how would custom software be layered in? Well, that depends. I mean, right now, we already have the capability of letting the user define their own content sources. If you have an internal, in your company, an internal RPM repository, or a public one that's third party, you can just define it and pull content from there and it'll be installed. We can embed containers at build time as well. I mean, any other ideas, we're open to suggestions about how to get custom software.
You can also drop custom files in Etsy.
Yeah.
So you configure whatever you want.
Yeah, you can also inject custom files at build time for the on-premise version. You can just write a file and it'll get injected at build time into the Etsy directory. Is there a question or am I out of time?
Question.
Okay.
First one, a follow-up to that question. Do you integrate with Ansible?
Do we integrate with Ansible? Short answer, no. Long answer, no. Yeah, there is in Ansible.
Yeah,
Oh, so Ansible integrates with us?
yeah, you can use Ansible to run OS build.
Right.
You can't run
Right.
Because you can customize it based on packages and stuff. Do some more configuration by dropping files in etc.
Yeah.
Running commands. That's why we are Ansible, right?
Right.
So that's actually what I was leaning for. It's like, with a lot of custom software, there's not only the dropping in files, but also like executing them
Yeah.
do things in there to prepare the environment.
Yeah, which is sort of what OS build is doing. I mean, not sort of. That's what OS build is doing. It's
But you can't have OS build in the or Ansible in the OS build environment. When OS build is building the image, it's not actually running. So it's not like some of the other build platforms where they run up the VM and basically install it.
how much? So first of all, how much time do we have? Because this seems like a discussion for over there, and I think there were a couple more questions if we have time to get to. There was one there before you. Sorry, can I get some? Go. Oh no, sorry. Start again. I didn't hear anything. Oh yeah, of course. Well, the question was if we consider other platforms, and yes, we can build. Okay, we don't have VirtualBox. Yeah, we have. Right, it's the same as lib. Okay, so we have VM. Yeah. Right, and that's sort of the thing, right? It's not just about making the file format correct. It's also about knowing what does this virtualization platform need. And you know, we're always expanding. We're always adding more stuff, and that's sort of what part of the reason we're thinking about this. We're rethinking about how we put these things together. Is that if, for example, we said, let's do Vagrant, right? We would figure out Vagrant for RHEL 9, and then it'll be like, and then we would be thinking, okay, this is libvirt for RHEL 9 x86, and then we would have to go through that again and redefine it for every configuration. And now what we want to do is say, okay, what does Vagrant need? It needs these things. We define them in sort of like a well-defined way and how they interact with the other components, and then you can drop it into any configuration and it should work. Question?
I have a follow-on question to his question, and if you feel like it's a rabbit hole, don't worry about it.
Okay.
But whenever I try to kind of do custom things, kind of like Neil described, I eventually defaulted to writing my own build stage, Python stage. Are there other options I should be considering in that case than just writing my own stage?
Oh, okay, so the question is, if you want to do something that isn't covered by OS build, you need to write your own OS build stage.
Writing my own stage, that's
Yeah.
all I've done in the past.
I mean, that's kind of the way to do it. Like if there's some kind of configuration or I don't know, there's something that needs to be run at build time that the OS build library doesn't cover with a stage, the answer is write a stage. But the best answer is write a stage and send it upstream, please, because we need them. All right, is that? No, it's not. Well, there's someone behind me, and I think you already, yeah.
I was wondering, you've shown us like the manifests.
Yep.
Right, then you've shown us web design. What if I want to like version control my image and just put it?
What if you want to?
If I want to version control my image definition, is like say find workload, define the distribution, whatever.
So the current state, yeah. The question was, we have the manifest, we have the UI and stuff, but what if I want to version control my sort of my configuration, my image type, or whatever you're doing? Well, the good news is the way you build an image on premises is with what we call a blueprint, which is a TOML file. And I'm out of time, but it's a text file. You can version it. We also support versioning. The way it works now, which might change soon, but you write a TOML file which configures the image, and you push it into Composer. And Composer itself also has a versioning system, but that might be going away. But it's text files. You can version them. And even in Cockpit Composer, which is sort of like the web UI that you run on premises, you can click through and configure the image, and then you can export that configuration as a TOML file and save it wherever. And I'm out of time. Thank you all very, very much.
Hi, my name is Clemens Lang, and today we need to talk about your use of root privileges in containers. I'll start out with a bit about me. I did study computer science in southern Germany. In 2011, got interested in open source projects while doing Google Summer of Code with the MacPods project. I'm using a Mac here. And after that, landed a job at BMW doing infotainment. So that's where I spent 7 years building infotainment for cars, first doing some software integration work, doing packaging. And this is where the connection to today's talk comes in. We wrote a 1,000-line of C single binary container runtime to simplify building software for a platform. And I got very familiar with the various namespaces involved in doing that. Then switched to over-the-air software updates for the entire car. I think we're the second in the market after Tesla to do that for the entire car. And for the last few years, did security at BMW, so Secure Boot and all that, you know, SA Linux, whatever you have. And that eventually brought me to Red Hat, where I now work in the crypto team. So first note, I don't do anything with containers in my day-to-day work, right? So this is sort of a talk from an outsider. And what I'm doing at the moment is I patch OpenSSL. I try to get rid of SHA-1 where I can. You know, that might have fallen on some of your feet recently. One of the culprits was me, probably. And I'm also dealing with FIPS certification, because that's a fun topic for everybody. So, root and containers, right? Before there were containers, there was some conventional wisdom that we always applied. If you run a service, create a separate user for it, just for separation purposes, right? And while, you know, then Docker came along and we started running everything as root again, because that's just what Docker did, but nobody thought this was a problem. And honestly, we still don't think it's a problem, and it probably also isn't that big of a problem, right? So just to put the entire talk into perspective for you. I brought an example here. Let's assume I create a directory in varlib, and then I bind mount that into a container. That container is running as root, so I'm running the entire command as root. And inside that container, I just happen to copy bin cat into that bind mounted directory and then run a chmod command to give it the set UID bit. So that means anybody who runs that binary now will get effective root permissions. And that also works outside of the container. So if I then outside of the container switch to user nobody, run that particular binary, and give it an argument of etc shadow, then I will get the contents of that file, even though the nobody user should normally not be allowed to read that. This isn't really a surprise to anybody, and it's not really a security vulnerability as is, because, you know, if you bind mount stuff in, then you should know what you're doing. So this isn't a surprise. But, you know, if we were running this with rootless Podman, then this wouldn't be an issue. You would still get a set UID binary, but it would be for that particular user that might not have privileges to do anything else. So we could improve by running this container as rootless Podman. Right, so running things as rootless Podman. That brings us to the issue of networking, because if you want to offer a service, then you probably want network in your container. And in Podman, in rootless Podman, there are basically two options. Either it's slurp for netNS, that works using a tap device, but has a couple of limitations. For example, you can only communicate among various containers via exposed ports on the exact same host or using the local host interface. And all the requests that you get will seem to originate from the IP address that's associated with a tap device. So you lose the information of where the request was actually coming from. And you might want to use that to filter, you know, for which IP networks you offer a particular service. Then there's some improvement on top of that, where you essentially take slurp for netNS, put it in a user namespace that owns a network namespace, and then do a common typical networking using NetAvarg after that. That's great, because it now allows you to do standard networking between containers, but it still uses the slurp4 NetNS tab device, so all requests still originate from the same IP address. So this isn't really ideal if we want to do is run a service. So the question that I was asking really turns into, can we run each container as a separate rootless Podman user, but with the proper networking, proper in quotes, as in the rootful networking, right? And that's the question that I want to answer today. And so you've now seen my motivation. This is the outline for the talk. We have to talk a bit about theory, but it will be quick, I promise you. And then I'll outline the various solutions that I found by following a mailing list post and a presentation somewhere in the Podman user group in 2021, I think. That was recently removed from the web server. Boo. I have to go to archive.org to get it now. Right. Let's get into it. Some theory. Why is it that inside of the container we can even read the file that's owned by root, right? To know that, we need to understand how user namespaces work. User namespaces they basically give you a separate UID range, and that UID range is mapped from inside the container to outside the container using a mapping file, and this is what this mapping file is. You can do this with pretty much every container that uses user namespaces, and it essentially tells you 0 in the container is user 1,000 outside of the container, and repeat this for the following number of UIDs, in this case 1. And then after that 1, the UID 1 is mapped to UID 524 something for the next 65,300 and something UIDs. This is what it will typically look like on a modern system where you have sub-UIDs. And the rule for accessing files is that containers, and I looked this up in the kernel, can't access inodes that are owned by UIDs and GIDs that are not mapped inside your container. So if you don't map the UID 0, then nobody can access root's files. It's as simple as that. So that's theory part 1. Theory part 2 is on networking. For that, you need to know that any non-user namespace is associated with a particular user namespace. And if you want to do an operation inside that namespace, then you need the required capabilities in that user namespace to do that. Sounds complicated, but it will be a lot easier once we get to the example. So managing a network connection requires capnet admin. That's the capability that the Linux kernel checks when you try to modify the IP address of a device, for example. If you now do this in a network namespace owned by a user namespace in which you are root, then you have that capability usually, and that action is allowed. However, changing the host's network namespace requires capnet admin in the host's user namespace, which is the root namespace that you typically don't see in configure, but it exists. And that also tells us something. It tells us if we want to use the real networking, then at some point we will have to have capnet admin in the root user namespace. So there's no way of doing any of this without using actual root. So for some pieces, we will need root. So my first idea when I was trying to do this was, okay, I'll start a rootful container, but Podman offers me this flag --UID map that allows me to configure which UID mapping I actually want. So let's just not map the root user from outside into the container, and then the problem that I was trying to solve is solved, right? This is what these lines here do. So essentially, I'm saying 0 in the container maps to the user that I'm currently outside of the container, and then the second UID map line just does the same thing with sub-UIDs, which we will ignore for now because it's, you know, we don't need to understand this to understand the concept that I'm trying to go for. So when I prepared this talk, I reran this command, and my heart almost stopped because I thought, wait, this didn't used to work. And this is the error message that I used to get when I did this. Turns out this is fixed in Podman 4.5, right? So this is what you should be doing. Thanks for coming to my TED Talk. Goodbye. Yeah, so, I mean, now this works, but I'm still going to tell you what I did before it worked. And there might be, you might learn a thing or two, and you might still want to not do this particular solution, but we'll get to that. So I did some Googling. I found a presentation that essentially said, yeah, you can run these 2 commands, then set up the network manually, and that should work. And here's a link to a mailing list post of a guy who probably did that at some point in time. And then I clicked that and thought, okay, this looks nice. I can probably do this. And the idea here is that all of this is as user now. So we are running rootless podman. I create the container. Note create, not run or start or any of that. I create the container without networking. I give it a name because we will need that name for the commands that follow. Right after, I run container init. That's also an interesting command because what that does, it sets up all the namespaces but doesn't actually start anything inside your container. So you have the namespaces available, then you have time to modify them, for example, to configure network, which, I did here in a script. Let's call it magic.sh. And after that, I run podman start, and my container starts as normal. So the question really is, what's inside this magic.sh? And it's this, and it's kind of a lot, right? Let's go through what this does. I will take podman inspect to figure out the PID of the container that we initialized but didn't start. Then this next, the sudo ln line is really just to give the network namespace a name that the IP utility from the IP route package can use. And then I do what podman initially or internally also does, which is set up a virtual Ethernet pair, move one side of that Ethernet pair into the container, then rename it into the inside of the container to ETH0, which is what we would expect the network's name to be, and then bring it up on both sides and configure an IP address so we can have communication going on. That is a lot of work, and note that we haven't actually, we had to do manual IP config for this, so I had to choose an IP address and set it. Then podman inspect won't know about this because we didn't use podman to configure the network. We must repeat this every time we start the container. And I haven't yet dealt at all with exposing ports, which requires writing firewall rules, which I really don't want to do manually. This is like tedious work. And yeah, I could probably write a script. But at this point, I was almost, I was about to give up on this because I thought, no, I don't want to deal with firewall rules and exposing ports. I don't want to. Let's just run everything with root. And then I thought, how does podman actually do this? Where's the code in podman that creates all these network interfaces and chooses an IP address and assigns all of this? And turns out there isn't. Because what podman does, it calls netavark for this and just pipes a bunch of JSON into it. And netavark takes care of configuring the network interfaces, moving them into the right namespaces, and so on. So I thought, can I just, create this JSON configuration, pipe it to netavark, and it will do what I want for me? And turns out, yes, I can. So I created a new podman network. You can give it IPv6 or not if you want to. I mean, we want to get rid of legacy IP, so you should these days. Then generate the required JSON that contains the IP address that you want to give the container, so we still have that problem. That contains the exposed ports, and then pipe that to netavark setup with a path that identifies the network namespace in which you want to do this. And then that will give you in return a name server configuration that you should somehow get into the container. I was lazy, I just wrote it to etc resolve-conf. Right, what does that JSON structure look like? Unfortunately, it's not documented, at least not in the netavark readmes or documentation, and also not in the podman documentation. So I reverse engineered it, and this is the rundown of what this is. It tells you, okay, I'm looking at this container ID with this container name. Here's a list of the port mappings, from which container port to which host port, how many ports, which protocol. And it also gives you a list of the networks that you want to attach to and which IPs you want inside that network. And This also gives you DNS. So you can get name resolution and service discovery if you also specify name aliases for that. And then there's this block network info here at the bottom that I omitted because it's really just the output of podman inspect on the network. Right, and this is the point where I show you that this works. And let's pray to the demo gods because I'm running this over Wi-Fi. And if it doesn't work, then I have a TTY recording of me showing this. So I have 2 shells here on a Fedora 38 system. Can you still hear me while I'm sitting? Yes, great. I have 2 shells here on a Fedora 38 system. One is root and one is the test user. And I said we want to start out as the test user, so let's do that. I want to define a runtime directory. Let's call our container rootless, and for that reason, I'm choosing that particular runtime directory. Then that probably doesn't exist yet, so I'm going to make it. And then I'm running podman create. And this CID file that I'm specifying here, I'll explain in a second because I automated all of this. I'm not going to do it manually now for everyone. Runtime dir, thanks. And that expects the ID of the container in this particular path. So that's why I'm creating it. Disabling network, giving it a name. And we're starting Fedora 38. And just for the demo, we're starting a Python web server on port 8088. Right, so this was created now. Now I need to run this container init command that we saw earlier. So podman container init and then the name of the container. That passed. And now we can see in podman ps-a that we have the container. It's in status initialized. It's not running yet, right? So let's get the PID for this. So we can see what's going on. How am I time-wise? I should probably skip some of this. Let's go to, yeah, I scripted some of this, and this is the part where we need to start running things as root. So as root, I have a script here that allows me to set this up. Now I need to use the exact same runtime directory that I used here. So let me copy this and fix it, because obviously id-u will return something else. Then I run setup. I specify a name that's used to generate an IP address. So in this case, I just use the container name again. Then I have a secret that I use so that the IP address isn't predictable that I'm generating. Test is the user that I'm running the container under. Then I want to attach this to the rootful0 network. And let me quickly check that this network actually exists so we don't get an error. It exists. And I want to publish a port. That's 80 to 88. So 80 is outside of the container, 8080 is inside of the container. And I could also specify a network alias here, but I'm not going to show you the resolution anyway, so let's just skip it. I mistyped something. This exists and container ID exists in there. There must be a typo. Where I don't see it, can? No, that's not the issue. I mean, at this point, this is the case where I'm stopping this and just showing you the recording because I don't have time to debug this right now. So we see the same thing, and now I'm sure that this will work, right? And the advantage is that I have time and I don't have to type, so I can tell you what's happening. So we already saw this, right? I'm creating the runtime directory. Then create the container. Without network again, I'm giving it a name. And we're starting the exact same Fedora 38. Container is created. Container is initialized. Then again, we see the status is initialized here. I'm getting the PID of that container because I'm, in this case, I'm going to show you some of the network namespaces. So what we see now is this is the process that's actually running, right? The container isn't running, but there's this crun process which initializes the namespace. This also lists the namespaces that we have. So if you have time to look at the details, you notice that the numbers are different behind this. So this means that the namespaces have in fact been created, both the user namespace and the network namespace. Right? And we can also see, and that's what this nsenter command is doing here now, we can now enter the namespace and look at the IP configuration inside of the namespace, and we should expect that there will just be a localhost interface because we told it not to set up any network. And that's what we see here, right? So there's no ETH0, no other network connectivity. Now is the point where I want to set up the network. So again, we see the rootful 0 bridge exists. That's the bridge that I want to attach to this container. Again, the path to the container, to the runtime directory that it created, setup to tell it to set up. Rootless is the name, the secret that I use to generate the IP address. Test is the user. Rootful 0 is the network name. Then publish, because I want to publish a port. And in this case, I'm also specifying a network alias that will be in the DNS server inside of the container. And this is the successful output. A lot of JSON. You don't need to understand it. It just gives you the network, the DNS configuration. And now we see, if we rerun this nsenter command, that the Ethernet connection exists at this point. Right, and if we want to, right, now we need to start it, obviously, because the process inside the container wasn't running yet. So I ran podman start rootless. Now it's running. And now we still need to test it because, you know, if we didn't test it, then it's broken, obviously. So I'm figuring out my own IP address and using curl to send an HTTP request to the Python web server inside of the container, and it works. So our networking worked as expected. I'll skip the stopping because we're running out of time. I also have this same thing automated with systemd. So I put the exact same commands in a systemd service file, and the lines that require root privileges, systemd allows you to just specify a plus at the beginning of the command, and that will run them with root. So that's a nice trick to get all of this in a single systemd service file. I'd show you, but we run out of time. So you'd have to go to the website where I published this. You don't have to scan the QR code now. It will be on the last slide again, so no hurries. And that also will contain this rootful networks Python script that I just used to do this. Right? So what did we achieve so far? We now have automatic IP configuration, even though I had to re-implement it, but the script does it for you. Otherwise, Podman would have done it. We can expose ports. With the systemd service file that I talked about, I can have this container controlled by systemd, and that takes care of correct startup and teardown. Podman inspect still won't know about this network because we added the networking manually. And If we try to use systemd notifications, that also won't work in this particular configuration because systemd will refuse the notify. It will see it, but it will refuse it. So what's next on this? Before Podman 4.5 introduced this, the working --UID map flag where this just works out of the box, I would have said maybe we should add a mode to Podman to drop all privileges except for network configuration. Now I'm not so sure. Honestly, if you're on Podman larger than 4.5, probably just use UID map to do the same thing. And maybe there's some improvement to be had for rootless networking. There's a talk tomorrow at 9:30 on rootless container networks get in shape with pasta. So if you want to give that a shot. Right, that's it. Thank you for attending, and any questions? Yes. Right, the question was, then the JSON format for NetAwark isn't documented, so probably not standardized. Am I afraid that this will break with the next NetAwark update? Yes, very. On the other hand, it's also a interface across two processes between Podman and NetAwark. So I know those two are developed in unison, but I'm at least hoping that they will preserve backward compatibility, and what I'm currently doing will continue to work. It also looked like somebody really wanted to document the JSON interface, just didn't. So I think that's the lack of time is the only reason why it wasn't documented. Yeah.
You demonstrated that the SUI trick escaping the container on the inode won't work because I think that will end up as SUI set to the meant UID. What about file-based capabilities?
So the question is, I demonstrated that the set UID bit trick won't work because it will map to the unprivileged user. What about file capabilities? I actually can't tell you. I'd have to look into the kernel source code what it does, but I'm assuming the rule that I learned from Michael Karist. He has a great training on all those isolation APIs. If you have a chance, attend it. What I learned from him is the general rule that you need the permissions in the user namespace that owns what you're trying to access. And if that principle holds, then it shouldn't be possible because in the user namespace that owns the files, which should be the root namespace, you as unprivileged user wouldn't have the capability to do that. But yeah, no, I'd have to test. Other questions? Questions from the internet, maybe? Then thank you, and enjoy DevConf.
Hi. So this talk is about RP filter, as you could guess. I believe most of you know what RP filter is, or at least have some idea about what it does. In this talk, I'm going to make the scope a little bit larger because I'm going to first start developing on what the IETF says about what I will call RPF. So I will make a distinction for the purpose of this call between RPF, the algorithms defined by the IETF, and RP filter, the Linux kernel implementations. And as we will see, there are several of these implementations in the kernel. So what is RPF? Let's say we have a router here in the middle connected to different networks. And with RPF, the general idea is that the router, instead of just routing packets depending on the destination address, it would also validate the source address of incoming packets. So here, for example, we receive a packet from network blue, and it will verify that the source IP address of the packet actually belongs to network blue and not network red. The objective is to limit problems caused by IP address spoofing on the internet. Let's say, for example, here we have an attacker inside network green, and this attacker wants to attack the victim in blue. So it sends a packet to the server in red, but instead of setting the source IP address with its own address, it used the IP address of the victim. So when the server receives the packet, it replies to the victim, and there are two benefits for the attacker. First, its IP address never leaks to the network, so the victim has no idea where the attack actually comes from. And also, when we choose carefully the server, we have a nice amplification factor. So the attacker can send just small packets, and the server would reply with much bigger packets. So there are protocols that are famous for doing that, like SNMP, for example. So this problem has been known for a very long time, and even some old RFCs like RFC 1812, requirements for IPv4 routers, it defines a basic algorithm to do some source IP address validation. Unfortunately, even at that time, it was clear that it would break some routing topologies, so it was recommended to not turn it on. Then came RFC 2827, which is more commonly referred to with the best current practice, so BCP 38 that it belongs to. BCP is just a collection of RFC. Unfortunately, this RFC didn't really provide any technical solution. It just talked about using access control list. It just said that source IP address validation was important, but it didn't say how to do that. But the IETF has continued to work on this problem, and we now have two other RFCs, RFC 3704 and 8704. And we will see what are the algorithms they define. So this first RFC defines 4 different flavors of RPF. We have strict RPF, loose RPF, ignoring default routes, and feasible reverse pass forwarding, feasible RPF. The strict RPF is really the simplest and most intuitive version. So here we have a router connected to 2 gateways, bringing to 2 different networks. So with strict RPF, what this router does is when it receives a packet from gateway blue, it will look at the source IP address. And if this IP address belongs to network blue, it will route the packet normally. And if it belongs to another network, either network red or it's not routed at all, it drops the packet. So this is the original idea that we found even in the oldest RFC. The problem is that it has always been clear that it would break asymmetric routing. So here, for example, we have two nodes, node A and B. They can communicate between each other between two gateways, blue and red, but node A is configured to only use a gateway blue, and node B is configured to only use gateway red. So when node B receives a packet from node A from gateway blue, it will do the strict RPF control, and it will realize that normally the node A is routed through gateway red, although it received the packet from gateway blue, so it will drop the packet. And same thing with node A. It receives packet from node B through gateway red, but it would route it through gateway blue. So RPF, strict RPF has actually broken communication between our two nodes. So another variant of RPF that was defined was loose RPF. So the loose version doesn't actually take the input interface into account. So it just verifies that the packet is actually routable, that the source IP address of the packet is actually routable. So in this case, we have, when the router receives a packet from gateway blue, it will just do a route lookup on the source IP address. And if the source IP address is routable, it will just route the packet normally, even if the source address belongs to network red. Obviously, if the router even has a default route, loose RPF is going to let almost any packet go, because as soon as it's routable, it flows. That's why we have the special variant of loose RPF ignoring default route, where the default route actually can't be used for the route lookup, but it doesn't really make any difference in practice. For example, in our case, gateway blue or an attacker from network blue could still spoof an IP address from network red. So the fourth variant of RPF that was defined in RFC 3704 is feasible RPF. Feasible RPF is interesting because it uses some extra information that were not used in the other variants. So we actually use all the information that are available through the different dynamic routing mechanisms. So let's say that we're using BGP. Here we have a different autonomous system. So at the bottom, we have AS0 that announces different routes, while here it's the same route. So it's 2001 DB8 A/48. It's announced to AS1 and to AS2. And eventually, AS4 learns about this route. And the AS pass is longer on the red side. So for routing purpose, AS4 doesn't takes the route from AS3 into account. But with feasible RPF, for incoming packets, AS4 would accept packets with source IP address 2001 DB8 A/48 as a source IP, even though it wouldn't use it to send packets because of feasible RPF and because it was announced on the other interface too. But that wasn't enough for all practical use cases. So actually, the IETF has continued working on this problem and has defined a new RFC, which is RFC 8704, with two new variants of RPF. So they're all based on the idea of a feasible RPF, but the algorithm gets a little bit more complex, yet even the acronym, as you can see, is getting complex. So the idea here is, again, to use the information we can collect with BGP. And instead of checking the the origin of the source IP address, we will check the reachability of the autonomous system that this source address belongs to. So for example, this is algorithm A, so that's the first algorithm defined in this RFC. We have AS0 that sends, that announces a route to AS1 and a different route to AS2. And finally, AS3 receives the announcement for both routes. And with this eRPF, the enhanced visible path RPF, will accept packets from any of these prefixes, no matter if it's received from AS1 or from AS2, because these prefixes both belong to AS0, and AS0 is the origin AS in both AS paths. And in practice, there are also problems with routes that are not propagated to all the autonomous systems. So the IETF has defined algorithm B so that a network administrator could work around this problem by putting interfaces into an interface group. So here we have AS0 who announce a route to AS1 and AS2. It's the same route, but AS2 doesn't propagate this route to AS3. But this is worked around with the administrator putting both interfaces into the same interface group. So now AS3 can send packets with source IP address belonging to this route. Even if it arrives from AS2, it will be accepted by AS3 because it's in the same interface group as AS1, and it would be accepted if it had arrived on AS1. So as you can see, RPF has become something much more complex and complete than just a simple route lookup on the source IP address. And we need some information that are not available by the kernel to actually implement them. Okay, so enough with the theory. Now let's see how the Linux kernel implements RP filter. So as I said, we have several RP filter implementations. We have one sysctl for IPv4, and then the IP tables, IP6 tables, and NF tables modules that all have their own implementation. So that's 3 IPv4 implementation, 2 IPv6 implementations. So here how we can configure them. You can see that in the slide offline. All these implementations support strict and loose RPF. There's a special option for loose RPF with all these modules. And beyond the limitation we already saw in the theoretical RPF algorithms, we have to face some kernel-specific problems. So first we have 5 implementations to keep synchronized, and we have the fact that the kernel doesn't handle IPv4 and IPv6 routing tables in the same way, and we also have kernel advanced routing features. So we'll see in detail what are these problems. So first, let's see just how RP filter interacts with regular routing tables. So here we have a route that is defined to use 2 different output interfaces. So what happens is that with most of the RP filter implementation, we can receive packets from any of these interfaces. Just the NF table IPv6 implementation only allows one of the interfaces. If we do the same kind of configuration, but with more recent commands, let's say, so we use next hop groups instead of a single route with several next hop, as we did before, we get the exact same result. So I'm not going to go too much into the details about why it's the case, but it happens that the problem stands in how RP filter handles ECMP routes, because what we did in these two examples is create an equal cost multipass route. So yeah, RP filter and the IPv4 and IPv6 implementation handle that in different ways, which leads to different results. Now let's see what happens when we define the same route twice, but with different gateways. So we can do that with IP route append, and let's see what happens. So this time we don't have an ECMP route. So what happens is that most implementations will only accept the first route, and only the IP6 tables RP filter implementation will accept packets from any of these interfaces. And again, that's slightly handled about how the kernel handles ECMP, even though we didn't explicitly want an ECMP route, but IPv6 internally converts these routes into a single ECMP route. And yeah, the rest is implementation detail. I'm not going through that now because we won't have time. Now let's see a more common use case, which is to define the same route but with different preference. So here we have preference 1000 and preference 2000. They use two different interfaces. Preference is like metric. You can use whatever the keyword, however you call it. It works the same way. So the favorite route is ETH0, and ETH1 is just the fallback route. So what is RP filter supposed to do? Should it accept packets on ETH1 or only on ETH0? The result is that almost all implementation accept packets only from ETH0. But again, IP6 tables behaves differently here. It's slightly related. The root cause is the same as for the previous example. This is because this implementation constrained the route lookup for IP6 RP filter. But yeah, again, that's maybe something we can talk about later if we have time. These are problems that probably could be worked on in the kernel, at least to make the different implementation behave similarly. But there are also problems that really are more fundamental problems and that are not only dependent on how the code is written. So let's talk about policy routing. Policy routing, for those who don't know, is when we use different routing tables filled with different routes, and we jump from one table to the other depending on some particular patterns. So here, for example, we have the main routing table that uses ETH0, and we use ETH1 for table 100. And we decide if we do our lookup in the main table or in table 100, depending on the destination port. So here, if destination port is 50,000, we jump to table 100, and if not, we jump or we stay in the main routing table. So let's see what happens. And in this case, what happens is that only the RP filter sysctl, so the IPv4, will jump to table 100. So it will route packets. It will accept packets from ETH1 if the source port is 50,000. So here, RP filter just swap the source and destination port, which probably is intuitive because actually that's what happens for the IP address. But we'll see that it's not always the right solution. And for all the other implementation, it's simple. The destination port is not taken into account, so we just never jump to table 100. So jumping to table 100 when we have source port 50,000 might look like the good idea, because when we send a packet to destination port, the answer will come back with the ports, source and destination ports swapped. But that's not always the case, especially with UDP tunnels like VXLAN or Geneve. We always use the same destination port, and in this case, this behavior is not appropriate. So let's do policy routing, but on something different. Let's use a packet field that we can't swap between the request and the response. So let's use the DS field. DS field is kind of like the TOS for IPv4 or the traffic class for IPv6. Those should be obsolete and should be replaced by DS field, but yeah, you get the idea of what it is. So let's see what happens and if there are some differences between our different RP filter implementations. And actually, all implementation work more or less the same way. I'll leave some details, but we can consider for this talk that they behave the same way. So what happens is that if the DS field from the return path matches the IP rule, then we do the route lookup in the table 100. So again, that probably looks intuitive, but in reality, the DSCP doesn't have to be mirrored on the return path. So if the return packets don't have the same DSCP value than the outgoing packets, we're not going to jump in the same table, and RP filter will break connectivity. And we can also do policy routing based not on IP packets or IP packets fields, but on metadata of the packets. For example, we could use the packet mark, the socket user ID, the input interface, and more, but we are only going to consider these examples. So packet mark. All of the RP filter implementation won't take the packet mark into account for doing their route lookup. Because the problem is that, again, we need to have the same packet mark on output and on input to get to jump to the right table. And often it's difficult enough to have the packet mark being symmetric on input and output. So we have to use a special options to make RP filter, no matter the implementation, respect the packet mark. And we have also problems with socket user ID. So we can jump to a different routing table based on the user ID of the socket that sends the packets. So that's for locally generated packets. But on the return path, of course, we don't receive the packet from a socket. We receive them directly from a network interface. And we don't even know yet on which socket it will be delivered. So all the RP filter implementation make the route lookup with socket or the UID, user ID 0, so as if it was sent by root. And for input interface, we have the same kind of problem. So if we do some policy routing based on the input interface, when we send a packet that has just been routed, we know on which input interface we received it. But on the return path, how should we do our route lookup? If we want to reverse input and output interface, then we should say the input interface is actually the output interface we would use, but this also is not known all the time. This depends on where the rule is on the netfilter hook. So that depends not only on the implementation, but also on where the rule is inserted. So to summarize the problem with policy routing, we have different set of metadata available in the transmission and reception paths. We have packet information that might be different on transmit and receive paths, and even for something as obvious as source and destination port, where we say, well, we should just swap the source and destination port, that doesn't work all the time. So really, we have a fundamental asymmetry between the receive and the transmission path, which makes policy routing mostly incompatible with RP filter. So to summarize the whole talk, RP filter, even if we consider just the theoretical part of it and only the IETF work, it's not just a simple on-off functionality. We have to select which flavor of the algorithm we want to use. For advanced algorithms, we need some cooperation with dynamic routing daemon. We might need for, if you remember algorithm B, some special configuration from the administrator. Also, we have to keep in mind that RPF was designed for routers and especially for ISPs, not for end host. And yeah, routing daemon, I talked about it. And then we have the implementation. So we have 5 different implementations for RP filter, which are hard to keep synchronized. We have all the complexity of how the kernel manages the kernel route lookups, and that has some side effects on the implementations. There are some things we could improve, like the handling of equal cost multipass, in order to make all implementation behave similarly. But there are also some fundamental incompatibilities with advanced routing, in particular every time, well, or many times where we use IP roles. Also, we don't support, and we can't really support currently the advanced RP filter algorithms, because we need some cooperation with BGP daemon. Okay, so thank you, and time for questions. Yeah, so the question is, can we detect if automatically if some IP rules are going to create problems when we use RP filter? We could at least detect that we have some special IP rules, and then consider this is a potential problem for RP filter. But the biggest problem is, yeah, what are we going to do if we activate RP filter and we detect that there's going to be a problem? Do we just disable RP filter entirely? Because there's no correct way for some of these IP rules. There's just no correct way to handle the problem automatically. We need some help from the administrator. Yes?
Is this primarily a means to avoid denial of service attacks on the internet, as you said, I think?
Yes. So yeah, the question is it primarily a mean to manage the problem, to handle the problem of IP spoofing on the internet? Yes. From the IETF point of view, and the reason why RPF was designed by the IETF, yeah, that's the main reason. That's really the reason. Yeah.
Does it then work if I configure it on the router on the internet? Because the attacker could come from the same subnet, which could be very huge, which is from the same subnet as the victim.
Yes.
So how does it then work?
So what the IETF recommends is that you activate RPF as close to the customer as possible, and if possible, even on the first router. And then if you have a very big broadcast network behind this, well, probably you also have also security problems. If you have a big Ethernet segment. Yeah, again.
Well, if it works for the routers, that's good. But why do we enable it on the end host then, on Linux? I mean, if Linux is not running on the router, but on the end host.
On Linux, we can activate it on a router or the end host. All RP filter implementation, they work similarly on the router, on routers, and on end host. It just make less sense on the end host, because if it's not going to change anything for the IP spoofing. Yeah, again.
Should we then disable it on RHEL by default because it's enabled there?
Yeah, okay, yes, repeat the question. The question is, should we disable it on RHEL by default? I know this question has been answered already some years ago, and it was said that no, we shouldn't disable it by default because it's security and we don't disable security. And there's no really technical argumentation. It's just a fear of accepting packets that were not accepted before. So yeah, the reason is this.
Because it's like forwarding. You could discuss whether it should be enabled or disabled by default. So it probably
yes.
Exactly the same umbrella. If we disable packet forwarding, we don't care about RP filter. If we enable forwarding, then we care. And what is the same default? Probably always deny, and if you as an admin want to allow more, then you allow. But probably, it's not going to change from the real perspective that we suddenly start saying, oh, let's our defaults to be everything is open, everything is accepted, let's forward everything, and let's assume that the admin is smart, because usually it's not the
No more question? Okay, thank you.